Very good morning to all of you, and we are in the day 2, and today we will start a new topic. In our last 2 lectures, we are mainly focusing on the review parts of thermodynamics, which are basic equations, governing equations, fundamental principles, and we need to carry forward those equations in our real application for combustions. So, in last 2 lectures I had given some glimpses of some concepts which can be used as a mathematical tool for combustion analysis. So, next I am going to start something on this topic, which is called as combustion and thermochemistry. Why we say it's a chemistry part is involved? Because in our thermodynamic discussions in our last things, when you talk about mixtures, so mixtures has its own identity before they are getting mixed, or substances getting mixed, and after also when they get mixed, we can find out the appropriate constituents in terms of their mass fraction, mole fraction, etc. But substance remains as it is. We can locate them in the reactants and after the mixture as well. But when you call as combustion, the reaction takes place between fuel and air, and the products are formed. That is what the chemistry concepts comes here. Normally, when you deal with the classical chemistry, we say reactants, products, and the reactions can happen among any kind of species that to form that products. But here our main chemistry focus would be that species that are involved in the fuel and in the air, and when they react, the final product that gets formed, that we need to quantify. So, that is the reason the word chemistry comes. So, combining thermodynamic aspects and combustions, a frequent word that is getting used is the thermochemistry. So, we will here also will start the our main focus for this lecture today is basic concepts of combustion and thermochemistry, how we can bring the thermodynamic concepts to the combustion systems. So, here we will discuss on this thermodynamics of combustions. We have reacting systems, then fundamental term that we normally use, the what is called as adiabatic flame temperature. The concept of adiabatic flame temperature use the word that during a combustion process, what is the maximum possible temperature achievable, which means if you assume that reaction is happening in a reactor and some reaction is happening in a reactor, and we do not allow the products to go out with a concept that we have a perfectly insulated wall, so that whatever after the reactions the heat developed through these reactions developed through this reaction, we can quantify them, what is the maximum heat that we can get. This can be done by constraining the wall, that heat is not supposed to go out of the reactor. So, that is the concept what we call as adiabatic flame temperatures. Then we will talk about something on how do you model a reactive systems. Now, when a reaction happens, there are the reaction happens in a very short durations, and in this short duration there are many kind of elementary reactions that are formed, but ultimately when it comes to the final when the reaction settles down, we get the products. So, and what under some equilibrium conditions we call this the products, certain products are formed. Fuel and air, when it gets mixed, it is supposed to give these products. When you say this, that is called as a situation chemical equilibrium. When the chemical equilibrium is formed, then whatever products that are finally settles down, we call them as equilibrium products of combustion. We call them as equilibrium products of combustion. There is another concept which we normally use, that what is called as water gas equilibrium. It has certain bearing that when for a combustion, any kind of combustion reaction, the final product is CO2 and water. If this happens, it happens, then we call this systems a concept called a water gas equilibrium. CO2 and water, they are in equilibrium after these reactions. Another important aspect of this combustion and chemistry part, when you talk about chemistry, the reaction can be exothermic or endothermic. Exothermic means heat is released, endothermic means heat is absorbed. But when you talk about combustion reactions, always you expect the reaction has to be exothermic, it gets released. Very rare situation we talk about endothermic, because sometimes the reactions, some species has formed at very high temperatures, but due to some reason temperature drops down and those species try to settle down by absorbing some heat among within the systems. So, those cases the system may be considered as endothermic partially. Okay. So, those are the some of the concepts that we are going to discuss in our today's lecture. So, let me brief about this, that when you bring thermodynamics into combustions, the synonymous word we use is the thermochemistry, and combustion situation is nothing new. It is a very old concept. We can see that combustion concept was existing since the existence of sun, because that is the oldest mode because of combustion which is happening billion of years ago and will be happening in future. But still we do not know what is the source of energy. So, obviously a combustion we have fuel and air. So, fuel somehow since we are getting energy from the sun, that means we can imagine there are plenty of fuels which are available in the sun, and that we are getting in terms of solar energy, we are getting these things. So, that means what I am trying to say, the concept is nothing new, it was a very old concept. Now, combustion concept comes to the human civilizations during the when we start burning the woods, when people see that fires in the jungles because of variety of reasons. So, those things were started with and wood combustion is a very is a solid fuel, and those combustions with starting point of that it spreads in variety of platforms. Engines, petroleum fuels, diesel fuels and all. So, with those evolution, the we can say what is the outreach of combustions, what was the outreach of the combustion starting from 100 years ago till date. So, that was one category of combustion. Apart from this, in our day to day life, we have cookings, we use LPG, we use in our transport sector, we use CNGs. Then there is another concept called porous media combustions, where the combustion concept comes only through radiation. And then this is about the application of combustions. Then moving to transport sectors, we started with IC engines, then we moved to gas turbines, then we went to rocket combustions. So, through which the combustion concept is used mainly for thrust generations. So, application is variety in variety way, just to harness the energy at the cost of getting some fuel and air mixing together or combusted together. So, basic concept, when we start the combustion concept, we require fuel and oxygen. So, in normal situation, nowhere we take oxygen separately to initiate combustions, as long as we are in the existence of earth. So, requirement of oxygen comes from the air. But when you go to outer atmosphere, you might have known these things, that we carry liquid hydrogen, liquid oxygen on the system itself, because at outer atmosphere, outer space or deep space, we don't have oxygen or air. So, basically in the atmospheric level, we take the advantage of air to get oxygen, and when fuel and air when they are mixed together with addition of heat, we get a tremendous amount of heat which is get released after this combustion process is over, and we get some exhaust products. So, identity of fuel and oxygen gets lost. So, we call this that some reactants, they give products, and when they and these reactants here, they are in the form of fuel and oxidizer. So, here oxidizer, I mean it is air as a whole, and we got this combustion products. Now, when you say combustion, what really happens there? So, how it initiates, and so this is initiated through a flame or non-flame mode. Through flame and non-flame mode means that when they actually there is a, when you create a spark or ignite, we try to see, maybe in our last lecture, what Professor Markus showed, that when you ignite, there is a flame plant that started moving. So, that is called as a flame. So, we introduce a term called as a flame, which gets which form instantaneously when we ignite the fuel and air mixture, and that flame travels in that domain. So, basically if you take a typical kind of IC engine combustion in a SI engine, so it is a flame mode. So, we have initially we have a unburnt fuel gas mixture here, and through this we create some spark, the flame gets generated. So, when the spread in the initial level, entire domain here is filled with fuel and air mixture. So, when you create a spark, a flame front gets generated. So, that is what we view or model the combustion phenomenon. So, this flame front tries to move. So, when it tries to move, because of its own strength move, it tries to compress this unburnt fuel and air mixture, and through this compressions the all subsequent fuels gets ignited. Now, this intensity of, so initially it is a flame. So, when this intensity of this flame gets increased and increased, we can emphasize them as a the flame front which is traveling at subsonic speed or supersonic speed. That way we can quantify as a detonation wave which is gets through this combustion. But initially the starting point of viewing this combustion initiation is through flame. Another way of is that which is a non-flame mode. Actually this and this flame mode of combustions is typically a concept called pre-mixed. Pre-mixed means air and fuel are mixed before it gets combusted. So, pre-mixed flame, that's what we sometimes we call this a pre-mixed flame. The non-flame mode type of combustions and diffusion flame, they are actually linked in a different way. Many people put it as a either diffusion flame, some people also call it as a non-premixed flame, but there are some concept here is that when you say non-premixed flame, what we see is that instead of the spark plug here is replaced with a fuel injector. When you have this fuel injector, what it means is that in this piston cylinder device, you are initially the compressed air is only compressed, and through this compressed air we inject the fuel. So, fuel sees a enhanced pressure and temperature environment. So, thereby the fuel gets auto ignited. When we say auto ignited, not necessarily that will have a particular locations, but here when you say flame mode, the flame prod gets initiated wherever you put a spark and that started moving. But here when you might have seen for diesel engine fuel injectors, we can put at various locations. Essentially speaking, we are creating multiple number of flames at a time and they try to settle down together. So, it cannot be categorized specifically a flame mode combustions. So, that is the reason we call this a non-flame mode combustions, because flames can be formed at many locations simultaneously, because fuels gets auto ignited. Fuel droplets which are injected, they got auto ignited. When they got auto ignited, when they find a similar quantity of ratio of fuel and air. So, we call this as the equivalence ratio. So, when those numbers are at par, so the fuel gets auto ignited. So, this is sometimes called as non-premixed flame. In many cases also it is interpreted as a diffusion flame, because initially it is a non-premixed flame, and this non-premixed flame also ignites the second layer of fuel air mixture which are subsequently. So, the flame front cannot be seen as a single front. It is a, so that is the reason the fuel air mixture gets diffused among themselves. So, we call them as a premixed. Internal energy in viewpoint, we say that system as a whole has certain internal energy, but here during a combustion, when you interpret this internal energy, it is associated with three major factors. One is translational or kinetic energy of species, which are constituents of fuel and air. Then we have vibrations, this together with the vibrations and rotational kinetic energy. So, essentially we are bringing down this energy or breaking the fuel in atomic level as well as molecular level. So, that is the reason internal energy is interpreted in this manner. And other aspect is that when you talk about this combustion, we normally refer for hydrocarbons only when you say it is a fossil fuel based combustions, which involves chemical reactions, dissociation, then their thermal analysis. Now, moving further, with respect to thermochemistry, we are also going to get acquainted with some terms, that is reactants, products and stoichiometric coefficients. I mentioned earlier that the reactants gives products, and to give the introductions that about stoichiometric combustions, when you write a chemical equations, balanced chemical equations, we introduce some terms like in this case H2 plus half O2 gives H2O. So, that number of atoms both left hand side and right hand side matches, which means that total number of moles of reactants and products here in this case are not equal, because here it is 1 mole, here it is half mole and it is 1 mole. So, this is way we, although number of atoms are same, but when you talk in terms of mole, there we write this equation in this manner: H2 plus O2 is equal to means here if you put in terms of their molecular weight. So, this equation if you write, so this is 2 kg of hydrogen and 16 kg of oxygen will give 18 kg of water. So, here masses gets balanced, and these masses are typically represented in terms of mole. So, mole is the term that we are going to look at when there is a combustion reaction. Additionally, we have to introduce this stoichiometric coefficients for a balanced chemical equation. Then we will move to some concepts of fuel. So, fuels are typically the fossil fuel, and they are mainly contain carbon, hydrogen and sulfur, and mostly the carbon constituents in the fuel is the major source of heat generations. And during a reaction, what happens when what we call as a complete reactions, we try to see that carbon reacts completely to form carbon dioxide with air, and hydrogen it gives to water, and sulfur tries to give sulfur dioxide. Now, why these numbers are formed, why these constituents are formed? Because when the reaction is done, so after the reaction is over, the temperature always shoots up. When it shoots up, the carbon is no longer in a position to remain as its original identity, it tries to find or combine with oxygen elements to form carbon dioxide. Hydrogen has to give water, mixed with oxygen to give water, and sulfur will have to give sulfur oxide. But at the end of the day, what we get is, if you do not get this, then we call this as a incomplete combustion. And here main culprits for this reaction, that if you do not get carbon dioxide, if you do not get water, and if you do not get when the sulfur forms sulfur dioxide. So, when we do not have carbon dioxide, it will remain as CO. Why it will be there? That your the reaction environment is not that convenient or ambience to form the carbon dioxide. So, this is how we should feel that how the reaction should go about. Coming back to fuel, I mentioned earlier, it consists hydrocarbons, and we can call them as a solid fuel, liquid fuel, and gaseous fuel. Solid fuels, we started with wood, but it can also go to, means if you are going to concentrate the energy with a small density environment, then we have to bring it in the solid form. Firecrackers, they are in solid forms. All kinds of solid propellants, they are also solid fuels. And for liquids, we have gasoline, diesel, kerosene, fuel oil, all they fall under liquid fuels, and we call them as liquid hydrocarbons. Again, when we say gaseous hydrocarbons, the major constituents we find them in the methane. So, what I am trying to say is that it is essentially hydrocarbons which are available in different phases. Then oxidizer. So, I mentioned that oxygen is required for every combustion reactions, but its usage, extracting the oxygen from air is not possible or lucrative. So, it is better that you take this oxygen from air. But when you take oxygen from air, air has these major constituents like nitrogen, oxygen, argon, CO2, so many other components. But major component is 78% nitrogen and close to 21% oxygen. So, initially when you look at fuel and oxidizer systems, if you take a fuel as a methane and it reacts with oxygen, it gives a CO2 and water. But since in actual reactions we are getting oxygen from air, so instead of this we write that equation in this form, like O2 plus 3.76 N2, and why that number comes? Because of this ratio. So, ideally speaking, they should give CO2, water, and nitrogen should not react. So, nitrogen comes out as it is. So, this is how the complete combustion reaction should look like. But in reality, this normally does not happen, because this is possible only when you have this is possible when this equation is balanced, and for this balanced equations we use this stoichiometric coefficients. But if the reaction does not happen to form in this manner, which means the composition or the stoichiometric coefficients of fuel and air do not match, then we will end up having different components. we may not form CO2, we may not form water, then what else will form? So, those cases we will land off forming this NO, NO2, because this N2 which has to be go as a whole, because of the elevated temperature, it tries to recombine with oxygen to form these kind of constituents, and they are actually the culprits for the air pollution. So, here we are going to use the word stoichiometric. Many times in this course also we will be using this term stoichiometry. Stoichiometric means it is the correct or exact air fuel ratio that is required for a combustion to happen, for a complete combustion. So, we normally use the term as air fuel ratio, or we also interpret in terms of fuel air ratio. So, here there is some logic here, that when you use the concept of IC engine, normally frequent term is air fuel ratio, frequent term is air fuel ratio. But when you enter into gas turbine combustions, people use fuel air ratio. There are some logic is that I mean it's both are same, interpretation for them is both are same, but what typical requirement for gas turbine combustions, because the those fuels are very costly. When they are very costly, people actually rightly trying to find out, instead of air fuel they call it as a fuel air, because they want to know that what is the exact quantity of fuel that is getting utilized, or what is the exact quantity of the fuel which is not utilized. So, in gas turbine combustions, the fuel air ratio becomes frequent, even rocket combustion as well, but of course they have using solid fuel. So, that way we air fuel ratio and fuel air ratio terminologies are same, interpretations are different. So, in one case we say air fuel ratio with respect to mass of air to mass of fuel, other case we say fuel air ratio with respect to fuel to air, MF by A, MA. Then there is a term called is theoretical amount of air. For a reaction to happen, I say oxygen plus nitrogen, they constituent, they form as air. To ignite certain quantity of the fuel, we require exact quantity of air. So, that air we call it as a theoretical amount of air, and that theoretical amount of air we call it as a stoichiometric quantity, that is a frequent term. This stoichiometric air, using if your combustion process does not use exact quantity of theoretical air, then mixture is treated either lean or rich. The word lean, which means everything that is with respect to fuel, means if it is a lean mixture, it is interpreted that fuel is less, air is more, and vice versa. So, fuel lean or fuel rich, those are the two numbers that we are those are two terminology that we will be using along with this stoichiometric value. Other ways of interpretation of percentage of excess air. So, if it is a theoretical air and percentage of excess air, which means it is a fuel lean, and percentage of defines fuel lean or fuel rich combustion, I mean, or percentage of fuel excess air means it is a fuel lean, percentage of deficit air means it is a fuel rich. So, so for example, if I say 150% theoretical air is equivalent to 50% excess air, which is a lean fuel, 80% of theoretical is equivalent to 20% deficit air, which is fuel rich. And all this air fuel ratio or fuel air ratio we write mathematically in this form. Let us say if we say air fuel ratio, it is Ma by Mf, and this Ma we can bring them to their molecular weight and number of moles. Then we find this particular number Na by Nf, we can say this is, by definition we can call this as in terms of molar air fuel ratio. So, that way we normally interpret our analysis, in what way we are interpreting, either in mole form or mass form. Then we see something in this term, like when the reactants are formed either lean or rich, we define a term what is called as equivalence ratio phi, and that equivalence ratio phi is based on the ratio fuel air ratio to the actual value to the stoichiometric value. So, in reality it can be fuel lean or fuel rich, but in actual case which is the actual case, in a stoichiometric case it is based on this, based on the fact that we get exact quantity of theoretical air. Then we introduce whether it is a fuel lean, phi is less than 1, when it is a stoichiometric, phi is equal to 1, and phi is greater than 1 when it is a fuel rich. But here the summary of these things is that when you have a fuel lean, we will get oxygen in the products. When it is a fuel rich, we get CO and unburnt carbon, unburnt fuel in the products. And rightly say that when you have a stoichiometric conditions, we get the maximum maximum energy, which exactly talks about the situation where we can find out the adiabatic flame temperature during a combustion process. So, this is some class examples how you look at methane air combustions for rich lean fuel and some combustions for rich fuel and so on. So, this is nothing new here, just to make a balance, and whatever I have said here, that in a stoichiometric combustion we get CO2 and water, and in a non-stoichiometric cases or fuel lean or fuel rich situations, we will have either NO, rich fuel we have CO and unburnt fuel, and in the lean fuel we will get excess oxygen. Then we have these products of combustions. So, for a situation where in a methane air combustions we get CO2 and water and N2 remains as it is, what we see is that in the products of combustion we get water, and when we say it is water, the analysis or interpretation little bit different. That one thing we say that if we take the products of combustion as a whole with CO2 and N2 without considering water, that is also possibility. Other way is that we take this water into account. So, those cases we call them as a dry product analysis or wet product analysis. And in some situations it happens that gaseous products of combustions in the mixture are cooled to a dew point of temperature. Means basically why this water is formed, that when the products of combustions finds an environment or a cooling environment, so that they try to condense with deposition of water, then we call this as a then we reach that reaches to their dew point temperatures. So, condensation gets initiated. Then we will try to give the introduction to the standard reference conditions when you actually deal the combustion mechanism to happen, and the standard reference mechanism could be either reference condition atmospheric pressure and reference temperature is normally done at this number. Why this is required? Because in our thermodynamic analysis calculations we require the formation of the products with respect to some references. Those formation of products are taken at these references if no, and all the data that are available in the books, they are with respect to the standard reference state, and mainly this data is required for computation of absolute entropy. So, here these equations I have shown in the last class, where we tried to define a mixture, and here we are saying that mixture is not a mixture, it is a reactants and products, and those reactions and products we are quantifying with their parameters, internal energy, enthalpy, entropy for each constituents, and try to make a balanced equation. So, what we see here, that while computing entropy, and all these equations if we find, we use this in molar form, number of moles for each of the species or constituents, and when it say this some species are formed, how it is formed, it has to be dealt with, because when you do the entropy calculation, it talks about the difference between initial state and final state. Now, the initial state and final state, when you do analyze for a mixture, it is easy that because they do not react. Now, when the reaction happened, your identity of reactants is lost. So, people try to interpret that how to find out this change in entropy. So, they started with concept that we have to take some reference value P reference and T reference, which is that reference conditions, you take that reference value as identity for calculation of entropy, and that from there you calculate the entropy change. So, the analysis gets simplified, because if you look at a classical thermodynamic equations, S is equal to S2 minus S1 is equal to this and it is entropy. You do not really bother about this term, we really bother about this R bar ln Pi by P references. But here we have to bring absolute entropy into discussion. This is enthalpy of formation. So, another term we say how do you get the enthalpy of formations. Now, in this, while defining this term, we are actually using the first law analysis, reactant products. So, something like here we say we have a reactor and some species that enter, and while going out we get the different things, but entire reaction takes place at these reference conditions. So, this means that if you say formation of C at this reference and formation of CO2 at this reference, so that those reference condition match between your inlet condition and outlet conditions. When they match, we frame, first thing we find out the chemical reactions, do their molar analysis, and then find out the difference between the enthalpy of formation, which is defined by this term H bar CO2 through these equations. So, ultimately for any reaction, enthalpy of formation of CO2, like in this case it is CO2, is nothing but which is heat transfer by number of moles which means this heat transfer can be negative or positive depending on exothermic or endothermic. So, that way we say it is the enthalpy of formation for that species. We say NO2 is formed, CO is formed with respect with C and O. Then with respect to that enthalpy of formations, because the word enthalpy of formation is with respect to species, but as a whole, when you take the fuel as a whole, we interpret in this way that we first think about what is the enthalpy of combustions. So, enthalpy of formation is with respect to species which is formed. Enthalpy of combustion is with respect to reactants and products. When you say reactants and products, you try to find out using the first law, you try to find out what is the energy content in the reactants and what is the energy content in the products. Difference between them gives the enthalpy of combustion. And this enthalpy of combustions is linked to the heating value of fuel. How do you interpret? So, so heating value of fuel, enthalpy of combustion is with respect to chemistry, but with respect to fuel we call them as a heating value, and heating value of the fuel it is interpreted in two ways. One is higher heating value, other is lower heating value. Now, when the analysis is done keeping water in the products, combustion products, and one case we call this as a higher heating value, and other case when the when you say higher heating value, it is obtained when all water formed by the combustion products is in the liquid form. So, that way the consideration of water formation is taken into account during the combustion process. Now, this when we say lower heating value, it is recognized when all water formed is in the vapor state. So, that means one case we say the formation of products without formation of water, and other case we say the formation of products and when water is formed or condensation takes place. That means the reaction temperatures, that means products are cooled below the dew point, their dew point temperature. Then I mentioned earlier that when reaction happens with some fuel and air, what we see is that if you enclose that complete environment, then we get a case where entire energy gets contained within that domain. Now, when those energy gets contained in the domain, the maximum possible temperature that can be raised through this process, we call this as a adiabatic flame temperatures. So, this is a adiabatic word is just a concept that to calculate the maximum temperature during a combustion process. So, this is also similar to this, using our governing equations, how one can calculate the adiabatic flame temperatures. Now, while calculating these adiabatic flame temperatures, what we interpret graphically in this manner, that entire energy of reactants gets transferred to products. So, when you start this enthalpy versus temperature curve for all reactants and all products, so they will go in this manner. That means, initially the reaction starts here at one point, slowly when the reaction happens, the number of moles of reactants come down, products formation goes up. So, that way the temperature also in this axis keeps rising, and one particular time when the reactants are completely burnt to form the products and we do not allow that heat to go out of that domain or reactor. So, So, those enthalpies are balanced. So, in those cases whatever temperature we reach, that is called as adiabatic flame temperature. That means initially we start with Ti and finally we arrive at this point, it can be maximum temperatures. So, this is how we analyze the adiabatic flame temperature in two ways. One is adiabatic flame analysis at constant pressure, other is at constant volume. So, I mentioned in our thermodynamic equation from the first law. So, if the first law is to be satisfied, that there is from the first law analysis we can say reactants and products they are equal, because I told that the internal energy is a function of temperatures. So, from the first law we start with internal energy for reactants and we try to say that they match, and while calculating that internal energy we bring initially they are at initial temperature Pi and Ti, and when final products are formed, it is formed at adiabatic flame temperature and final pressure. When this equation matches, then we can calculate the from this equation we can calculate these two values, one is at constant volume, other is at constant pressure. Okay. And this internal energy can be represented in terms of enthalpy as well, because U is equal to H minus PV. Okay. So, interpreting adiabatic flame temperature can happen in two ways, one at constant volume, other at constant pressure. So, based on this we have two equations. One equation is this, where we call this in terms of enthalpy, which is calculated, the adiabatic flame temperature is calculated at constant pressure. Now, having said this, adiabatic flame temperature calculation at constant pressure and constant volume, one can find out some of the important inferences, that during a combustion process when you calculate this use this word, we can say that adiabatic flame temperature gives the identity of maximum possible temperature, and that temperature, if you say you calculate at constant volume, it is always higher than that of constant pressure. And this has similar logic when you deal the analysis of Otto cycle and diesel cycle in an IC engines. One is a constant volume based combustion, other is a constant pressure based combustion. So, these are some of the inferences that we get out of it. Then there is a concept of absolute entropy. This part I have already explained how you are going to get it for a mixture by considering the reference point of pressure and temperatures. Now, coming back to modeling of reacting systems, there are two approaches. One is a constant volume modeling, other is a constant pressure modeling. So, in this constant volume modeling, we take care about main chemical reactions, how it happens, and this is a simple generic form of chemical reactions for hydrocarbons, where we say these subscripts of carbon and hydrogen in a general form A and B, and this A and B are and through this equation, putting A and B in some manner, we can frame a real combustion equations. So, while doing this, one can think of a constant volume based modeling, which allows the heat transfer as well as heat transfer into the systems, because we are through this process we are igniting. Other way that fuel air enters to a reacting domain. At the end of the day, we have some fuel sitting into here, air enters, when the heat is added we get the combustion products. So, this approach is a constant volume based modeling. And in a closed system modeling, normally we start with this kind of constant volume based modeling. For a closed system modeling, we get our analysis through this constant volume modeling by considering using the advantage of interpreting internal energy in form of in terms of enthalpy. So, in this equation we start with this equation, but somewhere this u value is interpreted as H minus PV. PV is nothing but your RT. So, these are the equations which are available in the books as well as in the slides. One can interpret in this manner. Then we have to deal with the entropy balance again for an open systems, and subsequently it can be interpreted for the closed system as well. And why I am trying to link is that all these equations which were given in our last lecture was used to derive this form, and here we are not going into the derivations, rather end use of these equations can be directly interpreted for modeling of any kind of combustion system. Here moving further, it is a closed system entropy balance. So, for that we need to recall the entropy equations from the thermodynamics, and assuming that reaction is going to happen in a closed systems with Q no heat additions. Okay. So, that way we did this, we have to do this analysis in that manner. And coming back to the chemical equilibrium part, when the reaction happens, when you have a ideal combustions, we have CO2, water, O2 and N2, but when we do not have those things, we have intermediate products like OH, CO, OH and N, NO, these are intermediate products. When such things are formed, and the final it is a these are the actually dissociated species, and they try to see another environment to form CO. If they do not see, they remain as it is there. So, if these are the things, so that means equilibrium has not happened. Now, moving further, this is a classical example how we say that during a chemical, when we say it is a chemical equilibrium situation, we land up having a case that when you actually view a reaction between CO and O2, it has to give CO2, but the formation of this CO2 from this, what actually initiated this reaction? So, initially we write this equation in this manner with a case that all of a sudden CO and O2 does not come together. So, when you see this equation, it is equilibrium equation. Had this equation been non-equilibrium, at any given instantaneous time, if you look at this equation, we introduce a term that at least 1 minus alpha, alpha and this. So, when alpha is 0, there is no formation of CO. So, this is how we introduce these equations separately in the modeling to this analysis, and that alpha we call them as a dissociation fraction. This is again same case, when alpha is 0, it means maximum heat release, when alpha is 1, that is no heat release. There are some significance of interpreting equation in this manner, because when the combustion modeling are done in the softwares or on your own. You have to start the equation, write the equation in this manner, putting its end conditions. Okay. So, this is a case where we try to interpret a chemical equilibrium situation for a simple reaction system from CO and O2, which means that when the reaction proceeds, we can see that how the fraction of CO2 gets dissociated, that means how this parameter 1 minus alpha changes during a reaction. Now, when you say it's a chemical equilibrium situation, which means that at that point of time entropy, because entropy drives the reaction, reaction proceeds in the direction of entropy. Simultaneously, we calculate the temperature as well as entropy. So, when we have, how do you calculate? I have told the reactions, the reactant and products you have to take different entity, each term you have to calculate, and for each cases you have to do the energy balance through this process, and we can say that entropy always increases in the direction of reaction. So, this curve we get. Side by side, when the reaction proceeds, temperature also increase because this dissociation fraction gets changed. So, this curve also keeps on increasing. At what particular time we have this final temperature, and this final temperature, if the walls are adiabatic, this final temperature can be interpreted as adiabatic flame temperature. Now, coming back, when the equation settles down, that means when equilibrium is achieved, which means that reaction cannot proceed further. So, we have achieved the equilibrium temperatures. So, the point at which we have maximum entropy, if you drop a vertical, then it will cut this curve and this will give you the equilibrium temperature. So, this kind of graphical analysis is mainly used, was mainly used basically when we do not have any other softwares or modeling approach. So, this is all I have already explained. That additionally, I have also forgot to mention that another term which is a Gibbs free energy, that many chemical, or normally we say Gibbs function. The Gibbs function plays a vital role during a reactions, because entropy is one parameter. Gibbs function gives a different approach which considers temperature and pressure as well simultaneously for this analysis for the combustion process. So, something on this already I told for equilibrium products of combustion. In this equilibrium products of combustion, for a if you say propane air mixture, one classical examples, the intermediate presses for these things are different, like OH, NO, and when you take this mixture globally, when equilibrium is achieved, we get this equation CO2 and water. This is a classical curve that talks about these equilibrium products of combustions for a propane air mixtures. So, here the significance of the curve is that in a single curve or single graphical representations, we can talk about mole fractions, we can talk about maximum temperature, also we can talk about the range of equivalence ratio in which the reaction is going to happen. So, if you see here, in reality, and for a propane air mixture, if you take ideally at equivalence ratio 1 you will reach this adiabatic flame temperature, but in reality that normally does not happen. It happens somewhere at phi is equal to 1.05. These numbers we get for a realistic experiment, and corresponding to this we get the flame temperature as 2278 Kelvin. So, for all IC engine application area, whether you do constant volume analysis, constant pressure analysis, your adiabatic flame temperature falls in this range. When you go to gas turbine combustions, these numbers will be different. This is one part. Coming back to the formation of the products. So, when you have equilibrium based combustions, we have CO2 and we have water and CO2. As you see that when your equivalence ratio is increasing, CO2 is also increasing, then it falls down because it does not find because the concentration or mole fraction falls down, and here similarly for these things. But this is what you see as a final entity, but before they form, before this H2 and CO2 form, already CO formation would have started. Hydrogen H2 would have reacted with oxygen. So, these are some of the intermediate reactions that gets built up during the initial phase of reaction. Finally, it settles down with this, but what we see globally is something like this curve and this curve as a chemical equilibrium equation. This is similar curve. Here also I mentioned about adiabatic flame temperature, and one point is that 1.05 is gives you the maximum temperature, but one point of time your water corresponding this highest mole fraction of water at equivalence ratio of 1.15, which means that this at equivalence ratio of 1.15, it is expected that we can get maximum mole fraction of water. These are same in continuation with that, there is nothing new, I have already explained. And the finally products of combustion, what we say here is that this is a complete picture that talks about all intermediate species that are formed during a lean phase of during lean phase and rich phase. So, in that case what you see, this curve shows how intermediate species like OH, NO, H, CO, NO and all this started, and they started with this at this point, and then when they keep on, when the reaction proceeds, this NO formation, and by that when the NO formation starts also, simultaneously OH and CO formation would have started. So, all the curves plotted together, which means that species evolutions during a combustion reactions, this particular graphical representation is going to talk about. So, this is nothing new here. And finally, lastly I will just talk about a water gas equilibrium case, that normally when you have end products of CO which is completely undesirable. So, many industry they talk about how to reduce this CO level, though they consider a water shift reactions, like they create an environment in the final product domain that CO, when there is a formation of CO and if it sees enough water, then it proceeds to formation of CO2. So, they create a typical environment at the product level, so that we can shift the propagation of CO to CO2. So, this is what we call as water shift reactions, and all in most of the industries they use this concept to reduce the level of CO, which is mainly culprits for pollutions. So, already it is time, maybe we can continue after this, or I will continue in this second half from there, because I have some more slides to show.
So feel free to continue from
Or maybe few minutes if it is there.
so last
Point I am coming back. So, here when you I mentioned about these water shift reactions. Now, while dealing with water shift reactions, another added advantage or added important concept is that we find the equilibrium constant, because when you analyze a hydrocarbon equations, fuel and air is taken with respect to oxygen and nitrogen, we arrive at these particular equations. When on such reaction happens in a situation that we have formation of CO, oxygen, H2, H2O, CO2, which actually means that these equations are getting modeled as if a reaction is going to happen in a generic manner, and all the products are trying to form simultaneously with this term. Then how do you evaluate those stoichiometric coefficient values? So, for that reasons we introduce a term Kp, which is called as equilibrium constant. This equilibrium constant normally we find with respect to ratios of various species that are formed. So, why this equation is required? Because by doing this atomic analysis, we can find out X, Y, A, B, C, D from both sides. So, one chart we can prepare: left hand side carbon, number of carbons, right hand side carbon, left hand side oxygen, right hand side oxygen. So, all these things we can find out, and you will find, and if you want to solve all the equations, you need to see that number of unknowns and number of equations are same. So, here to do that, what we that thing is coming here, that when for a given situations, when you have this particular case, we do this atomic balance, we find all the stoichiometric coefficients, then from there we can analyze all the total number of moles based on the unknown points of X, Y and Z. Then through this process we can get about the typical constituents of mole fractions of various species. One is CO2, CO and water. Okay. What I explained those cases, that when that reaction that happens, it is a lean and stoichiometric. When you have lean and stoichiometric, we have these products, CO and CO2. But when you have rich combustions, fuel is not getting sufficient air to combust properly. So, in those cases, so the reactions has to be modeled in a similar manner, we will have large number of equations like balancing C, H and O atom, we get number of equations is equal to number of unknowns, and through the introduction of equilibrium constant Kp, which is evaluated based on the values of partial pressures of each constituents. So, thereby we get a set of equations, and through that set of equations by doing this analysis we get this kind of curves. So, what I am trying to say is that when you generate these curves, actually background we are using all these equations that gives you a pictorial or graphical representations for variety of species formed during the evolution of a chemical reactions. So, this is all about I am trying to say in this lecture. There are some sample problems in this lecture. So, that can be used to get the understanding of what has been covered in these lectures. So, ideally at the end of these things I will just try to emphasize, although you see these equations, unless and until you try to do on your own, you will not get a feel out of it. For example, one case I can say, if you want to calculate the adiabatic flame temperature, unless and until you really do these actual calculations, you will not be able to evaluate these numbers. So, this is a case, specific case that talks about when you really use those enthalpy of reactants and products, try to map with the data books from the with data tables from the book, really calculate adiabatic flame temperature and two situations, one is constant pressure and constant volume. You will find that at constant volume value will be greater than the constant pressure. So, this is I am trying to emphasize, if you do it, then only you will get a feel of interesting approach. So, with this I will conclude. Thank you for your attention. Okay. So, we will have a
Thank you. Okay. So, welcome back to the second session concerning combustion chemistry. And you have heard a lot about this topic again in the morning in the part of Professor Sahoo. So there is of course some overlap, and sometimes it's important to get a different point of view on this topic. Especially if you are not familiar with it, I think it's very helpful so to get this explanation again, also from a different person. So I was really happy to see it in the morning. So in the last part we have discussed more the background. So we have discussed elementary reactions, global reactions, chain branching, chain propagation, chain termination, and so on. And now we want to put all these things together to get an reaction mechanism finally. So again, we have our simple system here. H2 plus half O2 gives water. We have our elementary reactions propagating, branching, and termination. So first of all, why is this so important to consider the chemistry? So one simple example are the classical ignition limits, or sometimes also called explosion limits. So we have in classical PT, pressure temperature diagram, and here we see the ignition limit curve. So at conditions left of this curve we don't see an explosion, and right of this curve we can see an explosion. And this is very typical, and for most of the combustibles you see a similar result, of course at different pressures and temperatures. But you see that if you sit on a specific temperature, here for example 800, and you increase the pressure, you start with no ignition at low pressures, then you come to an ignition region, and again at higher pressures suddenly it do not ignite anymore, and again finally you reach a third limit. And this is due to the interaction of mainly diffusion and chemistry. So at the very low pressure, the molecules, so we have very few, or we have a very low density at low pressure, and so the molecules diffuse to the walls, towards the walls, and at the walls they are more or less quenched. And so if you increase then the pressure, the density also increases, and therefore you have more collisions of the molecules, and then you are in a region where you have ignition, and then suddenly at around 100 millibar you find the next limit. So suddenly at higher pressures don't see any ignition anymore. And this is then now a competition of chain branching and chain terminating reactions. So the reaction H plus O2 leading to HO2 is a third body reaction. So an colliding partner is involved, and of course at higher pressures these collisions occurs more often, and so this competition between the formation of OH and the formation of HO2 at this point decides no ignition takes place. And then if you increase pressure further, you come to the third limit, the thermal ignition limit. So here density is so high that you produce so much heat per volume that ignition always takes place. So when we look now, for example, at temperature dependency at high temperatures, this is the most important reaction. So H plus O2 gives O plus OH, so chain branching, and this is the dominant reaction at high temperatures. Above 1200 K, this dominates the ignition process, and so the flame propagation and the ignition are both very sensitive concerning this equation. At intermediate temperatures, we have to consider this third body reaction, H plus O2 plus M leads to HO2 plus M. So this is then the reaction with is in competition with the formation of OH, and so this is the dominant reaction here, and also we have to consider this H2O2 decomposition as it leads finally to the formation of OH. So this HO2 plus, in case of hydrogen leads to hydrogen peroxide, and this hydrogen peroxide then decomposes, forms OH. So this is then at intermediate temperatures for a lot of species the dominant reaction. And then lower temperatures, for hydrocarbons especially, we have to consider very complex chemistry. So we have the formation of peroxides like described here. So it's very, 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 very sensitive concerning a lot of reactions. And therefore, so the high temperature part is easy to describe. So we need to know mainly this equation in detail, and then the rest we just have to guess some numbers. Normally that's enough. For the intermediate part we have to consider some more reactions, and if we have to consider lower temperatures, then chemistry becomes more and more complex, and we have to consider more and more reactions. So of course then the question, we have this H plus O2 gives O plus OH. This is the important reaction. But okay, where do these H atoms come from? We have H2 plus O2 at the beginning. So of course we have always fuel decomposition. So especially at higher temperatures, some H radicals will be formed. So, of course, different fuels have different decomposition rates. So we see different ignition delay times for different fuels due to this different, also due to this different H atom formation rate. So, for example, methane, C plus 4 hydrogen atoms is very difficult to ignite because it's difficult to abstract the first hydrogen atom. Propane is much easier to ignite because it's easier to abstract the first hydrogen atom. So we have seen this last time with the slide concerning the NOx behavior. So heptane shows has a very low NOx number because it's easy. Here we can easily decompose heptane and easily produce H radicals, which is, if you have more complex structures, not so easy. So, of course, then the molecular structure decides about the ignition process. This intermediate temperature chain branching. So okay, I have explained already in detail. So here, of course, then the formation of this hydrogen peroxide is the important part, and then we get the production of OH radicals. So now we have discussed hydrogen. Yes?
What was M? The M stands for M.
M is a collision partner, mainly water, but also oxygen, nitrogen, argon can also be a collision partner. So a partner which collides with our molecule, but do not, take part of the reaction, so it's not changed. So here we have a classical third body collision. So H plus O2, if they only collide, nothing will happen. So, but they need the third partner to bring them over the cliff, so that finally we will have HO2. So carbon monoxide, okay, the global reaction here is CO plus O2 gives carbon dioxide. But this classical reaction path, so CO plus O2, CO2 plus O, and CO plus O, and collision partner gives CO2. Of course, is possible, but this is a very, very slow reaction. But if only traces of water are present, we always have some OH radicals, and this reaction path here, so CO plus OH gives CO2 plus H, and CO plus HO2 gives CO2 plus OH. This is much faster. And therefore, for example, if you look for explosion limits of carbon monoxide, you always have to take care, is it dry carbon monoxide, or is it carbon monoxide with some humidity in presence. So you find totally different explosion limits here. Then the next molecule we have to consider is formaldehyde. So again, we have this global reaction. Formaldehyde plus O2 gives water and CO2. But of course, we have different reaction passes, reactions to consider here. So formaldehyde plus a radical gives an CHO radical plus RH, and so on. So different reactions have to be considered. And here, this formaldehyde gives carbon monoxide, which then can finally be oxidized to carbon dioxide. Now go one step further back. Now we will start with methane. So global reaction we have seen very often. CH4 plus 2 oxygen molecules gives water plus CO2. So when we look here, okay, CH4, when we look at the decomposition, one H atom is abstracted, so we have CH3. But then the question, how does this continue? And so here we see some possible reactions. So with O radicals, with OH radicals, and again with O2. And what you see, the end product here in this case is always formaldehyde. So we have seen when we start with CH4, we can yield formaldehyde, then we yield carbon monoxide, and finally we will yield carbon dioxide. So it's more or less a simple pathway. So here we have now the methyl radical and CHO radical as intermediates here, but this is the way the oxidation of methane in a flame occurs, at least for lean mixtures, because for rich mixtures there is another pathway possible. So there is a recombination of CH3 radicals leading to ethane or this ethyl radical. So and this then gives another pathway, and here we end finally with the CH radical, which is then oxidized to CO. So we have a quite simple molecule, CH4. We have normally a very quite simple pathway, but unfortunately we have to consider, do we have a rich or a lean flame? Because in richer flames this is a dominant pathway. The flame then of course looks totally different. So, and then of course we can continue to larger hydrocarbons. And again, we have to abstract an H atom at the beginning. So the hydrocarbon interacts with other radicals, giving this hydrocarbon radical and other molecules. And then we have normally this beta decomposition. That's the then important step. So the this radical we have here. So we have an organic rest here, this R, and here we have the radical position, and it decomposes in a way that this radical here in beta position is or split up from the original molecule. So we have this alkene, and we have the remaining radical. So and this goes down finally until we have methyl CH3 radical and ethyl radicals, C2H5 radicals. So even if we start with a very long hydrocarbon, so C16, cetane as an example, as a diesel surrogate, finally it's chopped down in small molecules, and at the end we will yield CH3 or C2H5, which again take part here. So here we see the pathway again. So we start with an alkane, we get an alkyl radical which decomposes, giving alkenes and smaller alkyl radicals and so on, and finally we yield CH3 and C2H5. So when we summarize the chemistry part we have discussed today, so we have H2 oxidation. If we look, for example, at CO plus hydrogen or traces of water, whatever, we have CO oxidation plus H2 oxidation. Then we have this methanol oxidation, this formaldehyde part we have discussed. And then we can add also this simple CH4, C2H6 oxidation. And finally, we have larger hydrocarbons. So if we want to examine the larger hydrocarbons, we have to consider the rest here too. But if we know this part here, we can use this also for the other molecules. So we don't have to examine this again. So, and then again we have to consider the temperature dependency. Again, at high temperatures, also for the larger hydrocarbons, this is the important reaction. This we have to know in detail, and this dominates more or less our chemistry. H plus O2 chain branching gives O plus OH. And in intermediate temperatures, so here from 900 K to 1200 K, we again have this different pathway. We form some hydroperoxide here, H2O2. This decomposes to OH plus OH. And this is then the dominant pathway at intermediate temperatures. And at low temperatures it gets really, really, really complex. So I have studied chemistry, but I'm not an expert in chemical kinetics. And therefore this for me is really not confusing, but it's, of course, you have to consider much more reactions. It's getting more and more complex because more and more complex molecules, especially this peroxide chemistry, gets more and more difficult. So here again, some details. So you have one peroxide already and add another O2 molecule. So we have some internal reconfigurations. You have chain branching, chain propagating. So it's very, very complex, and we will see it I think tomorrow with an example. These mechanisms then become, of course, bigger and bigger because you have to consider more and more species. But why do we have to consider it? So you can see this negative temperature coefficient, which is really astonishing, because we have seen that normally all chemical reactions can be described with an Arrhenius or as an Arrhenius equation. So we have an logarithmic dependency of the ignition delay time over the temperature. So here we have 1000 K divided by temperature. So we increase temperature from here to here, and therefore the ignition delay time should decrease, because linearly in this logarithmic scale we would increase our reaction rate in our Arrhenius equation. But suddenly, when we look at larger hydrocarbons, we can see a behavior like this. Suddenly, we increase the temperature, but the chemistry or the ignition delay time increases too. So these reactions seems to be become slower. And then if we increase temperature again, we will come back to our expectation. Increase of temperature reduces the ignition delay time. And this is here because the chemistry we have discussed before, we have different pathways. Different reactions are dominating different temperature regimes. So at low temperature, here maybe our peroxychemistry is dependent. Then here we have another reaction part. And then finally at the end, H plus O2 gives H plus O. The chain branching reaction dominates everything. So this is why we have to consider complex chemistry. So first of all, we can have lean and rich mixtures. So the chemistry can be not totally different, but different reaction pathways can dominate. And finally, at different temperature regimes, also different reactions can dominate. So totally influencing here, for example, the ignition behavior. So here we see it again. So at low temperature, we have this complex peroxy chemistry, and then here at higher temperatures, here it starts already with the hydrogen peroxide branching, and at the end here finally we would have this H plus O2 reaction dominating the chemistry. And this is of course a complex network of temperature, but as you see also of pressure. So especially then the third body collisions influence at higher pressures the chemistry. So how can we examine this behavior? So again, so here we have temperature and pressure. We have different regimes. So again, at high temperatures, we have this small radical chemistry. At lower temperature, this peroxy chemistry. We have to look, can we examine these processes if we probe for proper molecules. And here on these examples, we have to examine HO2 and OH. If this is possible, then maybe we can examine the ignition process in detail. So we can use, for example, a classical flow reactor here for the formation of HO2. So we have a reactor at a constant temperature in a range so below maybe 1000 K. And we have an inflow, the flow direction, and an outflow. And then we can examine, for example, the gas at the outlet. And this gives us, for example, information of this slow reaction. H plus O2 plus M gives HO2 plus M. At higher temperatures, where this reaction is dominant, we can use just a simple shock tube, where we can produce high temperatures and see very, very fast ignition events. So how can we do this? For example, we can use a specific laser setup. So we have here, for example, NH3 plus O2, and we use a laser to initiate the reaction, and we form some HO2, and which then can be detected. Here we have the detect the emission or the absorption. So we use a specific lamp here, and then the absorption at 230 nanometers is detected, and depending on the amount of absorption, we can get the amount of HO2. So using Lambert-Bersche law, so the light is going through our probe, and the absorption depends on the length of the cell and the amount of molecules in the pathway. So in a typical result we can see here, so the intensity as a function of time. So we initiate the reaction, and then we see how the HO2 molecule is formed as a function of time. Here we can see it at different temperatures, so the result for different temperatures. So a lot of experiments have been performed here. So with this, then we can finally get some more information. But we have to consider, when we have more complex configurations, like in this example, so we have complex peroxychemistry to consider. It can be very, very complex. Here we see it on the right side. We have different molecules at different energy level and so on. So we also have to use then complex modeling, which we will discuss tomorrow and discuss in detail next week. How to support chemistry here, or the experiments here, to get information about the reactions we have. And finally, one experiment where they have done this simultaneously. So we have one diode laser to examine the absorption of HO2, and we have a neodymium laser to probe OH, and finally we get results for this one specific reaction of cyclohexyl plus O2. So we can examine different pathways within one experiment. So, but okay, so we are not experts in chemistry, so this is of course quite confusing, but this is the reaction we consider here. So it's cyclohexyl plus O2, and we have different intermediates here to consider, and we can have different outcomes. So different radicals or stable molecules can be formed, and looking at our experimental results from the former experiment, we yield information about the possible pathways we have to consider here. But again, it's very, very important to consider we also have sequential and direct pathways. It's very sensitive, and we have to consider it in detail. Okay. So the same experiment here again. Here we use a YAG laser at 282 nanometers to excite our OH radicals. We have a flow reactor, and again we initiate the reaction using a photolytic oxidation of cyclohexane. So this is in a high pressure cell in this example, but the experiment is more or less identical with the one we have shown before. We use a neodymium YAG dye laser system to examine the OH radical, and here we have an X-hammer laser maybe to initiate the reaction. And so again we get time dependence OH signals. So the reaction, as I've said, was initiated at 193 nanometers. So at different temperatures, of course, we get totally different temporal profiles. But of course, with this information, again, we can examine our reaction here, cyclohexyl plus O2, to get more details. And finally, we have the possibility to use a mass spectrometer, which also gives, of course, very detailed information what is happening inside our reaction zone. So here in this example we have this flow reactor. We used again a laser to initiate the reaction, and then on the right hand side you see a mass spectrometer. So we suck some part of the mixture into a mass spectrometer and analyze then the mass of the different molecules we have in this specific region. So you see we have quite different experiments in different reactors, and all together we get information of the possible reaction pathway in total, but also for some specific reactions we can yield very detailed information about the reaction rate at the given temperature and pressure. So of course we have then to combine all this information to get finally an outcome. And the problem is, you can see here, when we look at global combustion mechanism, so it's a quite simple molecule, CH4. It's quite simple outcome, CO2. But we have a lot of different intermediates. We have a lot of possible pathways. So to describe CH4 oxidation properly, we need around 40, 50 species and 150 to 200 elementary reactions. So it's getting quite complex even for such a simple system. And It's getting much more complex if we have to consider soot formation. So we start with quite simple molecules here. So this is an pentane plus O2, and we get different intermediates at the beginning, and this form simple aromatics like benzene and so on, and this increase to PAH, and finally this coagulate together to form large soot molecules in a range of several nanometers. And so of course, when we consider CH4 oxidation alone, which is quite complex, if we look at this possible way, we have to consider thousands of intermediates and so on, thousands of different states, so it's quite complex to describe this. But of course, we can look at this beginning. This propagyl radical we have here is very interesting. So the reaction kinetics of 3C species at the beginning, this is very important for the formation of soot molecules. This propagyl radical C3H3 recombination is the first step to examine this. So this propagyl radical, due to recombination or addition, forms the first aromatic ring, and this then grows further on to PAH, and then finally to larger soot radicals. So here this is the molecular zone where the reactions dominate on the molecular level, and here we have a particle zone where also the collision of different soot particles may form larger soot particles. And of course, this initial part is very, very important. But again, we have to consider it's a multi-channel reaction, or we have multi-channel reactions with complicated temperature and pressure dependency, and but we need this experimental data to examine this theoretical considerations we have here. So how do these two propagyl radicals recombine to form finally benzene? It can again, of course, have different pathways. So there are then possible assumptions which we can see here. And then the question is, how can we examine this quite complex system? And again, we have the possibility to examine H atoms. We can examine propagyl radicals using UV absorption, and we can use laser-induced fluorescence and laser-induced incandescence to examine the formation of the larger radicals, so PA or larger molecules, PAH, and finally the soot itself. So first of all, we have to produce high temperatures, so we can use the shock tube again. We have to produce radical sources, so we can use different molecules here, and we have our detection schemes I have explained before, and we have to consider different temperatures, different pressures, and different initial concentrations. So this is in classical result we can see here. So again, the formation of H as a function of time, which helps us to understand this specific equation here, the second abstraction of an H radical from C3H4. So we can yield different reaction rates at different temperatures and different pressures, of course. Then we have the second, or the next abstraction leading to this propagule radical, again at different pressures and temperatures we can yield the reaction rates. So this is quite helpful, of course, to get information about these two important reactions. But then we come to the more complex situation, the recombination of two propagule radicals leading to benzene. And so here we can use examine the intensity. So we have propagule iodide, T3H3 iod, and this we photo ionize using a laser, and then we can examine the recombination of the formed propagule radicals, and so from this decay here we can get information about the reaction rate. And again, this is temperature dependent, pressure dependent, so we can see here a lot of results for this specific reaction. So I hope I have shown you that even when we have this very, very, very complex system leading to soot formation, we can, or we have the possibilities to look at specific reactions to get information about their specific reaction rates, and we can look at different steps of our reaction pathway, so the formation of our radicals. So here in this example, propagule radical, so from C3H6 propane, we have different steps to come here. That's the first important part, and then the recombination, the addition of two propagule radicals leading to benzene can be examined, and so on. So we have different experimental setups, or can use them to examine this. So flow reactor, I have explained already. We can use a classical combustion bomb, so where we have a premix mixture which we ignite, where we can examine pressure development, we can look for specific species, and so on. And we have this classical shock tubes where we have a driver part where we have a high pressure. Then we expand this high pressure in the driven part, and so we have a shock wave going through our system, heating up the unburned mixture. And normally we have this shock wave hitting at the end ball and going back, so heating up again our system. And this compression wave, shock wave, then initiates, of course, our ignition process. And we know normally exactly the final temperature before ignition takes place. And the last experiment is our rapid compression machine, where we can examine the ignition process at intermediate and lower temperatures. So we compress our mixture, giving temperatures in the range of 600 to 1000 Kelvin, and then we examine the subsequent chemistry which takes place. So this is a classical example of a shock tube. So at that time our ignition takes place, the ignition is initiated. So then it takes some time until chemistry decides, okay, I want to ignite, and we can then see a sudden pressure rise, and this is then the final, the outcome is then the ignition delay time for this experiment, depending on our initial conditions before ignition. We can use this combustion cell for forced ignition. So we have a spark plug here, 2 electrodes where we have an electrical spark, which then initiates our ignition. Here we can examine the ignition energy, we can yield information about flame velocities, but also we can examine some more complex chemical species, so OH radicals or sooting, or we can use laser techniques, for example, to measure temperature. So here an example, so we have here we initiate a spark. This spark heats up very fast our initial regime, and then, for example, at the beginning a pressure wave leaves our initial system. So we can examine, for example, how large is the spark as a function of time, and where is our pressure wave. And both quantities, so the radius of the kernel and the position of the pressure wave as a function of time, depends strongly on the ignition energy we use. So we can continue, check if it's working. No. Okay, the videos are not working, but of course we can ignite, try to ignite, in this example, propane, C3H8, and of course there is a limit value, minimum ignition energy. Below this energy we won't see an ignition, and with higher levels we can see an ignition. Then we can examine, for example, the flame front position from using, for example, OH LIF spectroscopy. Compare this with numerical results, and from this we can get, for example, the global flame propagation velocity as a function of mixture composition. So these experiments can mainly use to get finally laminar burning velocities. And we can use a laminar premix flame. So we have an unburned mixture coming from the left with a given velocity. And then here we have our reaction zone where the reaction takes place, and at the end we have our exhaust gas, and we can use, for example, again our mass spectroscopy to look at specific positions of this process. So to examine, okay, what is in our exhaust gas, but more important, which intermediates I can find in the reaction zone. So, for example, if we look at a typical burner at different heights, or at different heights, this way, sorry, for different temperatures, using different hydrogen amounts here, and then flow velocities, we can see, so the temperature depends on different factors, and also from this we can yield flame velocities, for example. So here we can see flame velocities for typical hydrocarbons, depending on the mixture composition, the fuel-air ratio we have. So near the maximum, or near the stoichiometric composition, we always see the maximum, and then the flame velocity reduces here for different hydrocarbons. But we also can perform much complexer experiments which SAT is set up. So here we have this mass spectrometer attached to our laminar premix flame, and we can examine then for specific configurations the amount of intermediates at specific conditions. And I think we come to an end for today. So we can use such a counterflow diffusion flame. So where we have an oxidizer coming from one side, the fuel from the other side for this configuration. So we have a flame which is for this diffusion flame configuration, they are located near the area where both flows meet each other. And of course, depending on our outflow velocity here, we have a stretch of this flame towards the outside. So we can examine, for example, extinction limits at which strain rate the flame no longer can exist. We can yield flame velocities, but again, we also can examine complex chemical reactions. So here, for example, so the strain rate and the equivalence ratio, when we look at this for H2R, we can see that at lower equivalence ratio and at a higher equivalence ratio, lean and rich flames, a lower strain rate is enough to extinct our flame, and at specific conditions, even at very high strain rates, we have a stable flame. So that's it for today. Do you have any questions? No questions? Okay. Thank you for your attention. So now we have lunch. At which time do we continue? 2:30. Yes. Okay. So thank you very much.
wide screen. Okay, good afternoon to all. We are now in this second day of this afternoon session lectures. In this lecture, I am going to introduce this combustion reactive systems, where we will try to introduce other conceptual reactions, which we normally call them as elementary reactions, global reactions. So elementary reactions are basically those reactions that are formed during the species formations, and global reaction that we see when the reaction gets completed as a whole. So that global reactions we in our previous lecture we dealt with, either it can be a lean mixture or rich mixture, in which you will find either CO or NO if, or excess oxygen, depending on the mixture composition. This is one part of the analysis. Then other part of the analysis is we will try to introduce this reaction mechanisms. So reaction mechanism which takes care that for this formation of elementary and global reactions, we want to see that what are the possible ways, depending on the pressure and temperature ambience condition in the reactor, what are the possible ways different species are formed. So in a certain situation, whether it is a favorable conditions for CO or NO, so that way based on this reaction proceeds. In some cases these reactions are either chain reaction or chain it gets also branched, so chain branching reactions. Next important point is chemical time scale. If you look at the instantaneous, let us say ignition. So ignition event lasts for about maybe nanosecond or maybe micro or nanosecond range. So in that ignition period, the combustion takes place. That means entire duration of combustion, if you take starting from fuel and air, when you start, ignition starts, all of a sudden we see the products as a whole, which is combustion products. But in between these two, formation of products, how fast it forms. So, what is the reaction time? So, one is the chemical time scale in which reaction gets over, fuel air mixture combustion reaction is over. Other is chemical time scale of those species formation. You can imagine if it is a long, it involves many number of elementary reactions and many global reactions to come out a typical time scale. That typical time scale is almost close to microseconds or still further less. So, there are some categorically we call this chemical time scale with certain definition. Then coupling reactions means there are different ways we can model these reaction systems, and some of the reactions can be I mean when you try to this when you talk about this coupling reaction systems, it is basically to analyze thermodynamic concepts how you are going to introduce for this reaction analysis. One such model is constant pressure fixed mass reactor. Other is constant volume based fixed mass reactor, well staggered reactor, that means it is a kind of a steady state mixing reactor. Plug flow reactor, it is something like it is a when the flow is taking place in a duct, flow is moving, at the same time we introduce fuel during the motion of the oxidizer or air. So, those analytical concepts are introduced here to talk about coupling reaction systems. But before you start all these things, the first point that I need to discuss is the Fick's law of diffusion, because that is the basic law that governs the mixing systems. So, in a combustion process, why this Fick's law of diffusion is important? Because it involves chemical kinetics, short duration phenomena or event that is going to happen. Second, to analyze the chemical reaction rate, and of course, during this thing, in addition to the heat transfer, there are also the concept of mass transfer, because normally in the thermodynamic analysis systems we have a fixed mass system or variable mass systems, but here additionally when species are formed, one species try to diffuse into others. What is the, I mean how fast it can diffuse? So, diffusion is just a concept that there is a perfume bottle is one corner of the room, but we can smell at every parts of that room, which means there are some mechanism mass transfer takes place from one end to other, and that concept we call as a diffusion. In this case the chemicals inside the perfume bottles tries to diffuse in the air. See, that means one gas tries to diffuse into other. So, the possibilities there are concept like we can have two species kind of diffusion. We can say we are trying to diffuse nitrogen into oxygen, oxygen into argon. There are so many possibilities. When this diffusion takes place, it takes care about the I mean how fast we are getting that effect is mainly based on the diffusion coefficient, and a diffusion coefficient is different for different gases, and some of the things we call them as a binary diffusion coefficients. So, that is the basics of Fick's law of diffusion, which talks about two things, one is mass transfer, other is there are possibilities that heat and momentum transfer can take place. So, mass, heat and momentum transfer will give you the complete spectrum analysis for the reaction systems. To do that analysis, mainly the mass transfer rate law for reacting gas mixtures is governed by Fick's law of diffusion. So, here the importance of Fick's law of diffusion we are trying to explain here. When you try to see conventional mass balance equation, and this Fick's law of diffusion is basically during a combustion reactions, some species is formed, some species disappears, so many permutation combination is done. Through this process, the main mass, the conventional mass balance equations gets modified. So, those modifications are introduced because there are two things we are going to see for mass conservation. One is mass, other is also species. Species also forms and disappears, but that identity of the species has to be there throughout. So, first thing is that we define this Fick's law in a manner that it says that if there are two species, basically here we are talking about this binary diffusion coefficients in which we talk about diffusional fluxes. The flux is nothing but what you are calculating the mass flux with respect to unit area perpendicular to the flow. So, if there are two species A and B, we are trying to define a term mass flux of species A per unit area perpendicular to flow, mass flux species for species B, which is again defined perpendicular to the flow, and adding these two will give you the total mass flux of the mixture. But means that when you talk about its density, it is a global density of the mixture. Now, once you know this mass flux value, we can easily define mass fraction, and this mass fractions in terms of Y A and Y B. And in addition to that, there are two parameters we are going to define. One is that is binary diffusion, binary diffusivity term. This is something like thermal diffusivity what you use in the heat transfer, similar to that. Its unit is meter square per second. So, if you look at this equation, this is something similar to heat transfer equations or Fourier's law of heat conductions. So, that there, but here we are through that modeling we arrive at the term this binary diffusivity term. There are two things, one is DAB and DBA. Identically they are not equal because the tendency of species A into B or B into A, it all depends on its own intensity. So, that way the terms can be values may be different, first thing. Second thing, there could be possibility of sign, it may be which depends on the concentration gradient, that can be positive or negative. So, that way we can find out this, we can simplify that equation in this term, and in this through this term we started with this mass balance equation, but ultimately we are going to arrive at another equation which is called as diffusional flux equations that introduces these two terms. The same mass flux species, this is the mass flux, but this is the diffusion flux, that comes due to the concentration gradient, and it is nothing but a function of density, which is a mixture, and binary diffusion coefficients for if it is A to B or B to A. So, these equations gets further simplified, and if you try to make an analogy between Fourier's law of heat conduction equation and diffusional flux equation, that means we start with a fixed law, and this fixed law gives another equation which is the diffusion flux equation, and this diffusion flux equation has some analogy or bearing with the heat conduction equation. If you try to compare heat conduction equations with these things, the terms are similar, and also since heat transfer always takes place from high to low. So, there is always a negative sign here, and here also higher concentration to lower concentration, and with some mathematical combinations, ultimately what we will end up is that when you say total mass is conserved, here also it gives another equation is total diffusion flux masses is also conserved, and this equation is always valid. So, when we talk about combustion equations for conservation of mass, one is we have to also say that diffusion flux equation also gets satisfied, which means total amount of species that are formed also nullifies the what is goes out. So, through this there are what I have told in these previous slides, they are based on the mass flux observations. One can also think of the Fick's law in terms of the molar analysis, where and there we call as a molar flux. What remains same, instead of mass kg we are talking in terms of kilomole or mole, and equations remains same. Then we enter into the next step, that what is called as reaction mechanisms. There are two types of reactions which we are maybe Sarah has also introduced. What is one is global reactions, other is the elementary reactions. First part is the global reaction, and global reaction means if you start the basic things like we have fuel, oxidizer, they give the combustion products. And when you talk about the chemical kinetics, we are more interested that what is the rate at which the fuel is consumed, and the fuel is consumed, which means that concentration of fuel, how it, because since it is consumed there is a negative sign here, so its composition comes down. So, this is the equation rate chemical kinetic equations, that how the fuel gets consumed. So, here that equations is normally expressed in this form. Here we introduce one term what is called as global rate coefficient Kg, which is a function of temperature, and one thing you notice that the concentration of fuel drops and oxidizer also drops, and there with this concentration raised to the power exponent gives the rate at which the fuel gets consumed. And the one thing to be noticed here, the when you say second order, third order things, M and N, they relate the order of reactions. How do you decide the order? If the reaction is of nth order with respect to fuel, mth order with respect to oxidizer, mth order with respect to oxidizer, nth order with respect to fuel, then the overall reaction will have n plus m. So, just add 2 plus 3 or 3 plus 2, it is a fifth order reaction, second order reaction, first order reactions. So, that way we make a judgment what is the order of reactions. Then we will try to move on to the elementary reactions. So, elementary reactions like we normally do not see these reactions when the equilibrium takes place. We start with a global reaction with this, we are more bothered about the, in this case hydrogen and oxygen gives water, and this water formation we are interested, we call this global reaction. And through this process, through this formation of water, there could be many possibilities among the combination of, since it is a very simple one, so we can find one formation is like during this formation of water there is a possibility of a free radical hydrogen atom or any kind of arbitrary molecule that can form, but which is not visible, but that aim. So, any arbitrary molecule would have formed, but somehow it gets consumed. So, finally, it does not show here. So, there are many, and also we may have hydroxyl radicals, hydroperoxyl radicals. So, these are kind of elementary reactions we do not observe. And imagine that all these reactions time scale is few milliseconds and a few microseconds, and during this microsecond we observe this reaction, but we do not see these formations. So, entire chemical kinetics is governed by this what we call as reaction mechanisms. Now, to analyze such reaction mechanisms, they are standardized in three categories. One is unimolecular reaction, bimolecular reaction, termomolecular reaction. That means, two species, unimolecular species A gives species B, then means a single reactant will give a single product, or a single reactant can give 2 or 3 products, that does not matter, but when you if this is the case, we in this case this is mainly true when you talk about these elementary reactions. For example, O2 can O plus O can give you O2, hydrogen can decompose to H plus H. So, these are kind of things which is unimolecular. Bimolecular reaction means two species try to combine. So, H2 plus O2 they can form this way, or H plus O2 they can form this way, OH plus H2 they can form this way. So, there are many possibilities like this, and each of reactions will have some term associated with that, what is called as rate coefficient. So, depending on unimolecular, bimolecular or termomolecular reactions, we can find out the rate coefficient for each reactions. So, this is actually required at the intermediate level, just to know how fast you are expecting the reaction to happen, and more or less this judgment is required, that when a combustion takes place, to how much time it takes to go from flame mode to non-flame mode to detonation, all these things analysis is required. Another important significant of this chemistry is this Arrhenius equations. So, this is a very standard equations that gives the overall picture, and this is mainly nothing but an experimental observations, and it has been found that this equations is true for mostly for bimolecular reactions. So, based on this, with which it is standardized in this manner. So, if it is a bimolecular reaction where A plus B gives C and D, so we can define this K Bi, which is, we call this as rate coefficient. Now, what is this rate coefficient? Possibilities that you can do, you have to do some measurement in that scale, experimental observations. But what this Arrhenius equation, he proposed a model in which the KT was defined in this manner, in an exponential manner. The rate coefficient he proposed that rest coefficient only mostly depends on the temperature. Because the reaction ambience depends both pressure as well as temperature, but his proposal was that let us say the temperature dominance is more as compared to pressure. So, it is the temperature that normally govern, and this philosophy happens to be true for all types of combustion reactions and with some experimental evidence. So, normally when you say that temperature increases, your chemical kinetics changes. One particular temperature, oxygen start dissociates, nitrogen and nitrogen start dissociating, that is for air. So, it is with this logic the Arrhenius equation was formed, and here the parameters that are of important is EA, which is the activation energy. A and B, there are some empirical parameters that govern at what equations we are looking at, and here we are going to use R bar, universal gas constant. And these activation energies for many standard reactions, already it has been tabulated for the activation energy. For example, for this kind of things, your activation energy you can find out this. So, this is already noted in the data book. So, accordingly one can take out use these equations, and these equations remains valid although it is empirical. Now, apart from this, we are now going to introduce another term that is called as equilibrium constants. So, there we said say rate coefficients. Now, we are going to introduce equilibrium constants. Now, to define this equilibrium constant, we take again similar type of bimolecular reactions, and here the reaction can happen in both the directions. A plus B can give C plus D and vice versa. So, it is a reversible reaction. So, for a reversible reactions to happen, what we see is that when the reaction is moving in forward direction, the concentration of A and B drops. So, accordingly the rate coefficient in the forward direction is negative. If same reaction goes in the reverse, it is positive, which essentially is that during a reaction some species are formed, but again they cannot remain in that stage because continuously, because temperature and pressure does not allow to react with other, they try to reverse back. So, those cases we may have, and one particular situation this equation can be modeled, that under equilibrium conditions we can use this particular concept that concentration of A with respect to time is 0. So, based on this we can frame a linear equations consisting of the concentration of each species with respect to the ratio of rate coefficients in the forward and backward directions. Now, next question, and since we say that for a given reaction this is again both are function of temperatures. So, people try to interpret in two ways, either as Kc or Kp. Kc and Kp, that means in one case we are saying that the reaction takes place at constant concentration or at constant pressure. So, that way we Kc and Kp are defined. So, either it can be Kc or Kp, and some situations you can observe that we will find the identical or similar range of values of Kp and Kc, and that is true mainly for bimolecular reactions. So, that is the one way we can say that for equilibrium constant for a bimolecular reaction can be found out by assuming whether we are getting it at a constant concentration or pressure. But in a reaction maintaining pressure is a better solution because we can control it, but we cannot control the concentrations. So, most of the cases for practical utility, it is the constant pressure which is followed to find this equilibrium constant. Another kind of reaction mechanism, many a case we use this steady state approximations. So, what this steady state approximations is that during some certain reactions, we really do not bother about how the reaction moves forward or backward, but what we really bother about concentration of one particular species during a reaction. We many a times we really do not bother about intermediate species concentration change and all, but we really bother about one particular case. So, for example, if you for this reaction if you try to see that what is the rate of production of nitrogen atom by using that previous concepts, and the reaction proceeds in either way. So, that way first equation we can find out based on the rate coefficient, and when we have a steady state concentration of nitrogen, if this number turns out to be 0, this number turns out to be 0 with a steady state concentration, that is an approximation. So, we are not looking at the reaction formation at any timely event, we are looking at steady state concentration, means during a steady state what is the how fast the nitrogen drops instantaneous. Basically we are not really bothered about instantaneous changes. During certain time frame we are looking at what is the average concentration. So, that way this equation can be modeled in this manner. So, we get steady state concentration of nitrogen. So, instead of bothering dN by dt at every time instant, we are really bothered about what is dNSS, steady state concentration with time. So, this is more easy way of handling these equations. Then we will try to move a kind of reactions, and most of the combustion reactions are chain reactions. So, it is a very short duration events, and these are like chain reactions. They occur in many chemical processes, and another thing is that we also introduce the term which is called as a chain branching reaction. So, it is often possible that concentration of one radical species can cause rapid formation of the products, which means that why we say chain reaction means how fast the reaction proceeds. Why this reaction proceeds? Because of presence of certain maybe you can say it is radical, that radical actually accelerates the process. So, through these things one can we call this as a chain reaction and this chain branching reaction. The analysis of these both the reactions becomes very vital to understand the combustion systems. To introduce such some of the things like how we can say whether there is a chain reaction or chain branching reaction. So, there are three basically category. If you have a global reaction in this manner, we can say when the pressure and temperature ambience is created, A2 tries to some molecule is formed, the A2 tries to mix with this and it tries to dissociate. Now, why it dissociate? Because this M is there, otherwise it would not have dissociated. So, this is a what you say chain which starts initiation. So, when it initiates and finally, when the chain has to be terminated, because once AB is formed, at that point AB is all of a sudden does not form, A becomes A2 becomes A plus A plus B2 can be AB plus B, maybe A2 plus B can have this, and each reaction will have different rate coefficients, and why it is initiated, maybe presence of certain molecules, maybe it may be a radical, or it may be a catalyst. So, that way we interpret this radical concentration that rapidly proportional to the pressure and chain reaction of major products. Then we will try to introduce the term what is called as chemical time scale. So, every event, every reaction takes place for certain duration. One event when you start, it has to complete. So, there is a duration for which we define the time scale. So, with respect to these reaction mechanisms, the time scale duration is hardly within a milliseconds. This is quite clear when you think about the combustion process in engines. Now, mathematically how do you interpret? So, what we call this as chemical time scale is nothing but a characteristics time, chemical time, which is required for any species concentrations to fall from its initial value, to a value which is equal to 1 by E times its initial value. Okay. So, if we try to interpret those things in this manner, we say that some species is concentration drops down with time, and how it drops down, it depends on its rate coefficient. Then further simplification, and if you integrate this equation, we write like this, and here we introduce a integration constant which is nothing but its initial concentration, and based on this we define a parameter which is called as a chemical time scale, such that the final when at any instant, if you multiply by with any instant, if you take this concentration value, when you multiply by its time scale and take the ratio with respect to its original concentration, you get a value of 1 by E. So, this is the definition of this chemical time scale. So, what it in other way, instead of rate coefficient, we chemical time scale for a reaction can be written in this manner. So, this is a unimolecular reaction, one can have it. So, there are expressions for chemical time scale for bimolecular reaction and termomolecular reactions. So, this is expressed in this manner. So, one can use this as a concept to find out the chemical time scale for a reaction events. Then you look into these reaction systems or coupling. So, by coupling I mean that for a given reaction systems, in our previous study we talk about the thermodynamics of mixture, then you introduced into the combustion systems, and that story does not end there, because that is a thermodynamic analysis of a chemical systems, but we have not introduced kinetics into that study. So, although we take it as a because all those are steady state analysis, but this chemical kinetic event is not introduced. So, when you try to do this study in a full fledged manner, and what we call as a combustion modeling, so we have to introduce its chemical kinetics of a reaction, which is based on the standard equation of this, how the concentration of fuel drops depending on the order of reaction, and with respect to other terms, the calculation of flame temperature, adiabatic flame temperature, calculation of enthalpy of products, reactants. So, that is when you couple these two equations to make a complete modeling, then that is called as coupling of reaction systems. So, we introduced the Fick's law of diffusion for species equation. We introduced chemical kinetics of the reactions. Then we already previously studied how combustion thermodynamically how we model the combustion systems. When we integrate everything together in a single domain and try to solve them simultaneously, we call this modeling to be coupled. So, there are three ways that when you basically four mechanisms in which we analytically study the coupling of reaction systems. One is constant pressure fixed mass reactor. All these words comes from the thermodynamics, constant pressure based, constant volume based, and both are fixed mass reactor. And when you do this, and they are perfectly homogeneous reaction. Then we have a well-stirred reactor, which is a steady state, steady flow and perfectly mixed. Then we have a concept of plug flow reactor systems, it's a steady state, steady flow with no axial mixing. So, why such modeling is required? Normally, in my previous lectures, I told that a reaction is modeled in a reactor, and in that reactor, if you assume the mixture is perfectly mixed, homogeneous, and we are using this equation, temperature is a function of time, concentration is also changes with time, and it is a constant pressure based reactor, then we call this as a constant pressure fixed mass reactor. I think this would be P, this is a constant pressure fixed mass, this is a constant volume, V as a function of time. So, the assumption lies here, whether pressure is constant or volume is constant. This is a one category which is normally done in most of the analysis. And there are some situations like which is called as well stirred reactor, means we in a given systems the mixing takes place, fuel air mixing takes place within the reactor, but simultaneously the fuel or air getting fed from one end and products goes out. This is another kind of modeling which is called as well stirred reactor. And other is like in some cases like what we call as a plug flow reactor. Many times so this is something like a piston cylinder concept, it is a kind of open system analysis. In some cases we feel that your air is moving and fuel is being injected simultaneously. For example, air is flowing in a duct. We can imagine that we are injecting fluid circumferentially, which means which says that there is no axial mixing. At every location, some locations we can inject fuel, so it is a circumferential mixing. And first mixture is formed with and we can put simultaneously mixture and it allows to flow through this. Such kind of duct flow analysis is mainly used for in the high speed engines, something like where we use ramjet and scramjet concepts. Normally air enters in a duct intake, what we call as intake or duct, and then mixing takes place as and when the fuel is inserted into the duct circumferentially at various locations. So, through this mixing we try to, during this mixing process we try to ignite. So, depending on the nature of your combustion, we can model this coupling reaction in this manner. So, we have coupling reactions, all the coupling reactions has to enter into one of the reactor modeling.
So those function of time and for a constant volume system.
Oh,
also
sorry.
is a function of
Okay. I think. Okay. So, this is how we model the coupling reaction system. Next thing is if you go bit by bit into this modeling, it is for this we need to develop the equation, governing equations for this constant pressure based fixed mass reactor, and by doing this and another point to be noted here, that the combustion reactions are mostly exothermic. During these exothermic reactions, the temperature and volume will increase with time, and through these things we also look into the heat transfer. So, main motive of this analysis for a constant pressure based fixed mass reactor, we need to find out at any instant of time, we are going to find out the temperature and species concentration. So, these are some of the governing equations that we enter by mixing thermodynamics or first law and calculation of system enthalpy, and finally we arrive at an expressions which talks our main intention is that how we have to find out how temperature varies with time, one thing, and how concentration also varies with time, either for species and as well as for global. So, these equations will let you know that in a chemical reaction, how species evolution takes place. Ultimately, the solution for this equation boils down to this particular expressions: concentration for any species I during a reaction and temperature with respect to time, and all these equation has to be, these two equations has to be solved simultaneously to arrive at the final conclusion. So, final conclusion I will, why I am saying, because as you see here, your thermodynamic equations are mixed with chemical kinetics, and those chemical kinetics means with respect to concentration, and when you because this to model these concentrations we require the information of equilibrium constants. So, those things are already introduced here to find these two important equations. In a similar way, we also boils down the constant pressure based fixed mass reactor. One thing is for how temperature changes with time and concentration changes with time. So, we are not going more into this. Then moving for the constant volume based fixed mass reactor. So, here we use the same equations, but with an assumption that because when you say constant volume, we are more interested with internal energy. That internal energy information we can get from enthalpy, as you did in the previous case. Enthalpy, which means it is a with constant pressure based analysis you find enthalpy, then introduce using this equation and arrive at the internal energy calculations. So, by doing so we have one equation how temperature changes with time, and then we have other equations how concentration changes with time. Of course, since it is and most of the cases what you see that when you do this constant volume based reactor, essentially speaking, that when you in a reactor the constant volume modeling is very critical, because we do not know how, because since we are fixing volume constant, we do not know how fast or what is the magnitude of level pressure rises within that container. So, there is a chance of explosion. So, here the word explosion comes into picture. When we do analysis for explosion, analysis has to be with respect to constant volume, so that we are actually simulating a situation of explosion. So, there when you say explosion, what you are trying to say, you have to see how pressure varies with time. So, that equation again comes from your temperature calculations, and that enters here. So, this equation is application finds during an explosion process. So, this is some of the case study that which any one of the textbook talks about, many standard textbook talk about. What is that? Whatever I have explained mathematically, and if they are modeled in one particular case, which is a simulation of a constant volume fixed reactor model for SI engine, to predict the temperature and concentration history, rate of pressure rise, knocking behavior, and that is for ethane air mixture. So, this can be done in this manner. That one thing is that you can see here how molar concentration changes with time. One thing we say, this side we have fuel, this side we have here we have fuel, and here we take about its scale change, and from this equation the rate of rise in the pressure with respect to time is modeled in this manner. This behavior is significant because although we really do not look into the chemical kinetic aspects of the reaction, but ultimately what you see during an experiment process for an SI engine experiments, we see in terms of how pressure rise with time, and it is a normal combustion, the curve should look like this. If it is a knocking cases, the curve gets an erratic behavior. So, why it is this erratic behavior? We say that seeing this pressure trend, we say it is erratic and it tends to give you knocking. But why this knocking happens? This knocking happens because how the pressure variation takes place in that modeling, by using that modeling. In this case, it is a constant volume based modeling. So, this is how it gives you an indication that how you control your charge or fuel air charge or concentration, such that we do not get out, we will get rid of this knocking behavior. So, main intention of showing this graph is that all these graphs are not just like experimental observations. Background thing, there are some combustion modeling that happens, and we can also model that behavior in this manner. There is another concept, is a well starred reactor, in which we talk which is a complete open system. It is a very complicated systems which involves mass, mole fraction and enthalpy which is entering for a given system, and same amount also goes out. And during these things, and the process we are looking at within this reactor, what is the global behavior of pressure, temperature and any species concentration or mole fraction. So, this is the sum of the modeling in which we try to see here modeling requires the knowledge of your Fick's law, mass formation or mass of species I and mass as well as species formation. So, through these things one can also infer the concentration of any given species and at its mole fraction. and ultimately we are interested for this kind of these things we get it from mass balance. Another equation we can frame about the heat transfer balance, and here one thing what we are going to think is that a mean residence time of a gases in a reactor. So, what it means is that we say that something comes in and something goes out. So, any gas which is formed in this during the reaction process, what is the minimum time it stays here before it gets out. So, that term is calculated by this number, which is the global parameter of the mixture involving density and its velocity and mass flux. And density we can find out your ideal gas equation with respect to this ideal gas equation P molecular weights and RT. So, in a plug flow reactor I am not going into details there because that analysis is complicated and it is a very short duration time scale event, and in which the mixing as well as combustion takes place simultaneously. So, in previous studies we first think about the here we whatever instant your fuel is injected here and those information and the information at this state. So, those informations are completely different because of the formation of the analysis is based on flame and non-flame mode, diffusion flame mode. But here it is not that way, it is the formation of shock waves because of the flow of air which is entering into duct. So, to give a global picture how a plug flow reactor analysis has to take place, one has to think about mass flux equation, we have to talk about species flux equations, energy equation and momentum equation. By studying these things in a complicated manner, we are trying to, of course, the analytical modeling, all previous thermodynamics analysis will not work out. We also have to link to gas dynamics analysis into this. Classical thermodynamics principle will not work here. We also have to talk about the effect of shock waves in terms of pressure, temperature rise into this reaction system. And we can see the kind of complexity of the equations, how the density changes with space. Space means different locations you have a different density. When a different density means flow is no longer incompressible, it is compressible. So, also the temperature also changes with respect to time, that every locked location temperature also changes with time. So, there is no point in doing it in analytical modeling unless and until one has to put frame the equations for a given for a particular situation case. So, this is all about I need to talk about this, and these are some sample problems based on our understanding today over these lectures. One case we talk about ignition delay calculations in using these systems, well-starred reactor systems. Okay, here we try to introduce a piston cylinder concepts to calculate mainly for this is normally standard equation engine kinetic analysis for an for a IC engines, and in this engine kinematic analysis we are more interested that how your total volume changes with clearance volume, which is a function of compression ratio and other engine parameters. So, that equations we are going to analyze here to calculate the ignition delay fuel cutoff studies. So, these terms I will come back when you deal with the fuels, ignition delay and all these things. But what I am trying to say, the nomenclature, engine nomenclature has definite bearing in terms of the ignition and the calculation and thermodynamic analysis for the reaction systems. So, with this I conclude. Thank you for your attention. Okay, sir. So, you want to take over, or I mean we will start this discussion, or we will take a break? Yeah.
So, without a break, we will continue.
Please ask them if they need some break, maybe another 10 minutes, 15 minutes, we can start. So, my part is over. I think after that he is going to present his work, and today we have any other who is going to talk today? No. Then you have enough time, then we can open for discussion as well. Okay. So, we will take a break for 15 minutes. After 15 minutes you can come over, and maybe you can initiate the discussion, he will present. Okay. Thank you.
So I thought I have to include these similar models in my presentation too.
Do it.
But
Nothing.
no.
No.
I thought, and now I see you have done it, so I'm happy that you have done it. So I can.
No. That you take it as an independent manner, because the way of presentation, mine and yours should I talk. किससे?
I have to start. Okay.
Okay. Hello. So very good afternoon to all. So today I am going to talk about my research, PhD research topic actually, that was the film cooling system design. So these are the table of contents like film cooling overview, then the history of the turbine blade cooling, and the cross flow overview and the factors affecting the film cooling, followed by the experimental design, how to design the experimental setup for a film cooling application, then the numerical modeling approach for the film cooling problems and our key findings, and then the research publication we have in this area. So what exactly is film cooling and why we use film cooling? So component which is generally under the pathway of the hot flue gases like the gas turbine blade and the afterburner of aero engine and the nozzles, which is generally subjected to the very high temperature, and to protect the component from the thermal stress, high thermal stress and failure, generally we eject a coolant through a surface hole, and which forms a thin protective layer over the surface and prevents the direct exposure from the hot flue gases. So generally the combustion product, in order to increase the thermal efficiency and power output, the temperature, inlet temperatures of the gas turbine have increased significantly over past few decades, and to protect the all components like combustion liner, the afterburner and the gas turbine blade, we eject a coolant through the surface. Coolant may be the air, may be the kerosene, or may be the any other fluid which is at relatively at a lower temperature. So this is the history of the turbine blade cooling. So early 1980, the metal temperature was not very high, so there was no need of the sophisticated cooling technique, and after 1970 the cooling technique, there is a necessity of the cooling. So the film cooling and other cooling techniques, like first it was the other cooling technique like the regenerative cooling and other cooling, conventional cooling techniques were evolved, and nowadays the film cooling, among all cooling methodologies, film cooling is the most commonly used technique to protect the metal from the hot flue gases. So the history of the film cooling was basically, the idea was generated in 1946 by Whitgard, which was basically used in the high altitude, the aircraft facing the issue of the ice formation, and to melt the ice he suggested and to inject hot air and to melt the ice formation, and from there itself the idea of the film cooling was generated. and these are the common factors which affect the film cooling performance. So mainly we have the geometry related parameters like the shape of the hole, ejection of the secondary steam, so the angle at which the secondary steam is ejected with the main stream, and the shape of the hole also. So we have the different kind of holes, ejection holes, and the surface of the geometry, like it may be the aerofoil shape, maybe the corrugated or flat surface. Depending upon that, the stability of the film cooling depends. And the other parameters like the blowing ratio, so it is nothing but the mass flux of the secondary stream to the main stream, and then density ratio, which is basically the ratio of the secondary stream density to the main stream density. And third parameter is the main stream flow Reynolds number. Basically in practically it is the Reynolds number of the main stream flow, or you can say the hot flue gas Reynolds number, and then the turbulence intensity. So these are the some common parameters which basically affect the film cooling performance. Apart from there, the other parameters also which on which the film cooling depends, but these are the common parameters. Next is the jet in cross flow. So jet in cross flow is closely related to the film cooling. So whenever a secondary steam enters into a cross flow region, so due to the pressure difference and combined effect of the pressure and shear, the secondary stream is basically splitted into the two rotating counter rotating vortex pairs, and that is commonly known as the kidney vortices. And that kidney vortices basically increase the mutual induction and causes the lift up of the coolant from the hot surface, and basically degrade the cooling performance. So with this cartoon one can see the number of vortices commonly generated for the jet in a cross flow. So the horseshoe vortices are basically generated in the nearby the secondary stream, and the wake vortices are basically in the wake region, which is initiated from the surface itself and extended up to the counter rotating vortex pair. And shear layer vortices are basically accompanying the counter rotating vortex. So these shear layer vortices and wake vortices are basically the unsteady vortices, and the counter rotating vortex pair and these horseshoe vortices are basically the steady vortices. So coolant ejections hole shape. So there are different holes were generated with the time passes. So initially the film cooling was started with the slot ejections, and but due to the slot there was a sufficient decrement in the material strength, and then it was preferred to introduce the cylindrical hole ejection. But as you can see in the previous slide, we have already shown that because of the mutual induction of the kidney vortices, there was a coolant lift off issue with the cylindrical hole. Then shaped hole was introduced by the Haven, and in case of the shaped hole, the hole is basically diverged in both lateral and the mainstream flow direction, and because of that the additional pair of the vortices are generating, and that vortices basically counters the effect of the kidney vortices. So basically the jet lift up is completely mitigated by the introduction of this shaped hole. And another way to mitigate the effect of the kidney vortices is the branching of the hole. So in case of branching, a main stream, a main hole, and side by side two branch of the additional holes. So the side holes also generate the vortices that nullifies the vortices formation in case of the cylindrical hole. And this is the setup, that is the setup I have designed during my PhD in NIT Manipur. So the setup consists of a subsonic wind tunnel facility, and there is a open circuit wind tunnel and the main stream and secondary stream flow. So in case of the main stream flow, the main stream is basically a heated air. So we use the electrical heaters to heat the main stream flow, and the flow straightener, by the flow straightener and through the test section main stream will pass, and through the pressure regulator mass flow controller, basically the secondary stream, which is as lower temperature, or you can say the ambient air, is supplied into the film cooling surface. So our study was mainly focused on the corrugated surface, So these are the common testing, means the blade can be used, any shape can be used for the film cooling, and the temperature profile can be recorded with the IR camera. So this is the picture of our setup actually. So this is the mass flow controller and the pressure regulator, and the setup was basically the insulated with the styrofoam and glass wall to maintain the uniform temperature throughout, because there was a temperature loss, and we have installed the electrical heaters also at the front of the suction. And this is the calibration for curve for the boiling water for the IR camera. So IR camera was first calibrated with the thermocouple. So both readings, for to calibrate the IR camera we use a copper tank, and that copper tank basically painted with the matte finish black paint, and the IR camera was focused on the one portion of the black finished copper tube, copper tank, which is filled with the boiling water, and the water was boiled using the resistant heater, and the other side of the wall is temperature is measured basically by the thermocouple. So thermocouple was pasted, means fixed at the other side, and the one side temperature was measured by using the IR camera. So both once the water was heated, and they are allowed to cool the water, and with the passage of time the temperature was recorded through the IR camera as well as the thermocouples and plotted for the cooling of the water. And this is the comparison of the thermocouple measurement. So generally we calibrate the thermocouples reading with the IR camera before going to read the measurement of or take the measurement from the IR camera. So these are the position of the thermocouples. So near the hole region there is a high gradient of temperature, because main stream and both secondary stream are mixing. So main stream at high temperature and secondary stream at low temperature. So the temperature gradient will be high in near the just downstream of the secondary hole. So as we move on the downward direction, so secondary stream will be completely mixed up with the main stream. So accordingly the thermocouples are arranged in the downstream direction from the jet to the secondary stream to the further downstream directions. So just we have compared the measurement of the IR camera or IR camera and thermocouple measurement for the flat plate. And this is how we do the uncertainty analysis. So for a sample case we got the 12% of uncertainty, and this is just the this is basically the effectiveness formula, T main stream minus T wall temperature and T main stream minus T secondary temperature. So both main stream and secondary stream temperature we use to measure with the thermocouple, and the wall temperature we measure with the IR camera. So camera we use having the resolution of 320 by 240 pixels, and this is the uncertainty of the individual instrument, like flow uncertainty. So pitot tube, mass flow controller uncertainty, and the temperature uncertainty recorded by the IR camera and thermocouples are basically the 2 degree and 0.5 degree. This is the numerical modeling. So we have a lot of options for the numerical modeling, and we can use the right from the RANS model to the DNS model for modeling the film cooling problem based on the adaptability and accuracy required. So whenever we require for like vortices and other capturing of the other sophisticated flow physics, so we can go for the higher order turbulence model like LES or DNS or more unsteady RANS. But sometimes the domain size is bigger, so computational cost and the time will increase, so we prefer the RANS. So we have done in our study both, we have used RANS and LES both models, and this is the accuracy basically of the modeling approach. So once if suppose we are using the DNS model, so it will resolve all the EDs, and if you are using the LES model, so it will only some extent of the EDs will be only means directly resolve, and some portion of the EDs will be basically the model. So for that we have the idea about the size of the vortices generated in the flow region. Based on that we can modify our mesh. So we basically prefer to find out first the size of the eddy generated in our region or flow domain, and based on that we modify the mesh, and the mesh resolution basically we express in the non-dimensional Ward coordinates in all three directions, and we have the comparison given with the others study also, kind of similar study in the LES. And this is the symbol of the mesh we are using, and we have done the grid test. This is the unstructured mesh basically generated in the ICM, and this is the way we calculate the grid uncertainty. So if we have a refinement factor like R21, like grid 2 or grid 1, there is two different grids. So we have some refinement factor, and based on that we will find the grid sensitivity index like GCI based on the apparent order of accuracy. And this is our key findings, like in the first, this is our one of the LES study we did. So this is the one node below the cross flow region. We have taken a section, and this is the forward and reverse ejection basically comparison with the forward cylindrical and shaped hole. So in both the cases we can see that directly there is, this is the average contour taken by the numerical study using the LES model, and you can see the completely in case of reverse ejection the velocity field is completely shifted to the rear end, or you can say the trailing edge side of the flow. And another study, one of our study was related to the slot ejection. So that was basically to check the whether we are ejecting the locations, different locations. So what will be the impact on the flow stability, or you can say the film cooling performance. So we use different locations like L0, L25. So these are the different possible locations we have chosen, and based on that we find out the film cooling performance. So these are the different, because these corrugated surfaces are highly used in the afterburner of aero engines. So and during some specific situations like combat takeoff and takeoff from the short runway, basically the extra amount of fuel is burned in the afterburner, which is generally situated at the rear end of the aircraft. So in that condition, due to the burning of the extra fuel, there is a significant rise in the temperature in the afterburner section, that around 200 to 300 Kelvin. So that causes basically, that requires basically a thermal protection. So their film cooling can be applied. So with that aim, we have taken a corrugated surface for the investigation, and different locations or different combination of the holes we have used. And this is our this is RANS based study, basically experimental and RANS based study. So these are the vortices which is generated. So once we are changing the location, so the vortices formations, or you can say the recirculation is also changing, and that causes basically the mixing of the, so our desire is that the secondary stream least mix with the main stream. So once it will mix with the main stream, it will not protect the surface. And this is the another study that we have done, basically that is the corrugated sinusoidal corrugated surface and the forward and using the reverse ejections. So that was also a experimental and numerical study, and this is the result of a numerical study. You can see in the forward ejection also, you can see the kidney vortices are forming in a plane perpendicular to the main stream, and which is completely mitigated with the reverse ejection. And you can see the vortices are in planar, some kind of vortices you can see, that is the planar vortices which are generating basically in the plane of the corrugated wall, and the vortices are absent in the wall normal direction. And based on the temperature profile or thermal protection we are getting through this film cooling analysis, we have done the thermal stress calculation also, and because of the reverse ejection is better as compared to the forward ejection, both on the flat surface also as well as the corrugated surface also. So there is a significant reduction in the thermal stress can be seen. And these are the publication we have done in this area. and these are the work of my PhD thesis and master thesis. Both were basically on the film cooling area, and presently I am planning to work in the multi-phase flow heat transfer, fluid surface interaction and combustion. Thank you.
Questions? Or shall I start with questions?
Yes, I have. So how do you finalize the positioning of the holes on the blades, on the blade periphery?
Actually, we have not done the experiment on the blood. We have done on the flat and corrugated surface only.
Numerical analysis, I think you have shown something.
No, in experimental we have shown the possibility actually in the back slide. No? This is the flat surface. This is just for the possibility that you can measure the blades also. You can the.
No, I didn't understood.
Huh.
This is the blade profile,
Mm-hmm.
and the holes what you have approximately,
Mm-hmm.
where you have placed it.
Actually, I have not done a study on the blades, so I have just put it this picture for the that sample that you can put the blade analysis. But based on my experience, I can say you need all around the blade. Blade means all around the blade you will put the hole. Means the performance will be different on the pressure and suction side.
And what you have shown is for only plates.
Only flat plate and corrugated plate. Basically, our aim was to investigate the afterburner of aero engine. So there only the corrugated surfaces are mainly used.
Exit nozzle, right?
No, afterburner, as you can see. Oh, actually, I need to go back. This is the afterburner. This there you can see. This portion we are actually focusing.
Okay.
Okay, I have a doubt in the calibration part. Can you go to slide 11? Yeah. So can you explain just there are so much deviations and you are just talking about something and you are attaching the thermocouple at a place and you are using the infrared camera.
Yeah. No. We have calibrated our thermocouple before using to the air gun.
Yes,
Yeah.
that is what I am asking. The process, how is it calibrated? So that is
Okay, process. So first we calibrated our thermocouple. So we use basically based on the temperature range. So our temperature range was close to the 60. So we used the T-type thermocouple. So these thermocouples are basically hole inside the plate. The plate was basically the nylon plate, and that plate, based on there is a glue which is called the what we call it as non-thermally conductive glue. So with the help of that glue, we just inserted through a pinhole. We inserted the thermocouples, and we focused the IR camera also on through the IR window, and we recorded the temperature, and we measured the thermocouple temperature also. And based on that, this is the comparison we have done.
Means I think what was the exposure time for this IR camera? So is it instantaneous temperature or it's a steady state temperature?
Once system is reached to the quasi-static conditions, then we started our recordings.
Then in that case, that much of deviation should not arise because if both are at steady state, then their temperatures should really match.
No, deviation will come because thermocouple will have some error, right, or uncertainty. IR camera also have some uncertainty that will come. Actually, we are measuring in the flow, so in that way deviation will come. You are not.
That is why I asked.
Yeah.
Is it instantaneous temperature?
No, actually in the flow field, no? So there will be chances of difference, like in if you are measuring in a steady wall or somewhere, so there will be exactly the same temperature you will get. Like in the boiling case, we have measured using both of the IR camera, and that you can say there is difference hardly less than 1 degree.
The plate, what you have chosen, have you placed it? It's a post-flow condition or it's a natural flow kind of thing? You have done some experiment, I think.
We placed our, like this is the setup actually. So you can say the plate was kept like this, and in that plate we injecting the coolant through that.
Post flow condition.
Yeah,
Post flow condition.
and the main stream is flowing, which is the heated air.
Okay. Thank you.
Can you go to, I think it was slide number 2. Oh no, this one, 4.
Hmm.
4. Is it this plot from literature?
Yes.
Yeah, because the unit is not correct. So degree Kelvin is not a unit.
Yeah.
And the temperature you are showing here, this is the temperature without cooling.
Yeah, without cooling.
Yeah, so okay, so the need for cooling. Then I think it was slide number 6.
Yeah.
So you show here the injection angle.
Mm-hmm.
How is it defined? So
It's the angle between the main stream and the secondary stream measured with reference to the plate.
yeah, at which position?
Yeah, position is, this is for the flat plate actually. So position is that we have a lot of the holes.
Because
Means,
this is the angle. So on the right we can see it maybe better between the counter-rotating vortex and the surface. So at which position in this counter-rotating vortex are you measuring? In the center, at the bottom, at the top?
Basically, this is the counter-rotating box appearing this.
Yeah, but how would you define the injection angle?
Ejection angle.
Yeah.
So this is the angle between the, this is the main stream flow directions,
yeah.
and this is parallel to the flat plate, and this is the secondary flow direction. So this is angle between these two actually.
Okay, it's on this line.
Yeah.
That means if you change the
Injection position.
the angle of the nozzle, you would also change this injection angle.
Yeah,
Yes,
if,
okay.
yeah. If we change the secondary stream position, means angle we change, then the penetration will change.
And how is this? On the next slide, you have shown the variation of the inlet, the shape of the inlet.
Yeah. This one.
Does this not also very strongly influence the, not the injection angle, but the mixing at least?
Yes.
Yeah.
But there was significant reduction in the strength of the material, so that was actually absolute after some time. So it was the beginning of phase of the film cooling basically.
Can you go to slide number 10, please? So here again the unit.
Oh.
The unit is 0 degrees Celsius. What does it mean?
No, that is wrong actually.
Yeah, so the unit is degrees Celsius.
Yeah.
So why we have this 0 degrees Celsius?
No, this is not 0, this is a error actually.
Yeah, because on the next slide you have also used this. Maybe can you continue?
Yeah.
So flow without heat transfer means you have not used non-heated air.
Yeah, we are not using the heated air.
So you see, you have done this experiment in not in Germany. So we seldom have 30 degrees Celsius ambient temperature.
Yeah.
So it's warmer here in India than in Germany.
Yeah, we have done in the experiment at Manipur actually.
Yeah. So what is the maximum temperature of the heated air you can reach?
Actually, through our heater, we will be able to heat 62 degrees centigrade.
So when you then look at your slide number 4, where you have talked about temperature of 2000 something Kelvin,
Yeah.
how can you compare your results with the conditions in an afterburner?
Actually, for the validation, we have used just this experiment, and numerically for the parametric study, we are going for the high pressure and temperature. Once we validate the model, then we go for the higher.
So you want to use these ambient condition experiments to optimize your numerical setup and to validate
Yeah.
this. Okay.
At low, basically low density ratio.
Yeah. Can you show please slide number 11 again? you have here a Mach number 0.5 and 0.
This is blowing ratio actually. This is blowing ratio. This is a similar kind of thing, that is blowing ratio. In film cooling, it is the ratio of secondary steam mass flux to the main stream mass flux.
So when we have, so in second case you have higher secondary mass flow than on
No.
the left.
M is 1 means the both secondary and main stream. Comparing to this case, this case have higher flux, secondary flux.
Yeah, but the cooling is not so good. So you have more secondary flux, more cooling flux, but the temperature is higher.
Yeah. Because at a high blowing ratio, generally the lift off, actually the stream is lifted, secondary steam is lifted from the surface. That is the main issue with the higher blowing ratio. At low blowing ratio, it will be remain attached to the surface. Once you increase, it will directly penetrate and behave like a jet.
Is this then represented by M equal 1?
Yes?
Yeah.
It has already been discussed in many of the literature actually, that at high blowing ratio, it's penetrate into the main stream.
Yeah, but this high blowing ratio, is this then represented by this M equal 1?
Yes, yes.
You said this is the ratio of
Yeah, yeah.
primary and then secondary. So if we have a very low primary flow and a very
It depends upon the hole shape actually. Suppose we are using the shaped hole. So in that case, at M is equal to 1, there will be no lift off from the surface. If you are using the shaped hole, diverge hole. But if you are using the cylindrical hole, after 0.9 or something, they start, means many of the previous researchers have reported, like Goldstein and others have reported.
Yeah, this I understand. The question is then the separation, so you don't have gives the blow ratio here.
It's
This maybe the more important
means
quantity.
blowing ratio. This case is given 0.5 and other case is 1. 1 means I think you are thinking like that. It's both are equals. Then how can be possible to means lift off from the surface? I guess.
Why the cooling is not so good, and the explanation is you have lift off.
Yeah. So for better cooling, the attachment is required. Better detachment from the surface.
Yeah, but so if you reduce both velocities,
Mhm.
you also have M equal 1.
Yes.
But then you don't have any lift off, or?
Yeah. In that case, means there is a balance between the density ratio and the blowing ratio.
Yeah.
So there is optimum value at which the jet will be completely stick to the surface. Otherwise, it will be lift up from the surface.
Yeah, yeah. Now, therefore, the question isn't. So I don't see any information about the blowing ratio here,
Yeah,
or the velocity, flow velocity.
which case? Only we have given the blowing ratio information here, and we have defined in the beginning itself.
Then you have these CFD results,
Yeah,
the
yeah.
2D plots. Can
Yeah.
you please show it again? No, yeah,
This one?
this one.
Yeah,
When we look at the right at 0.5,
yeah.
uh,
Which one? A, B, C, D.
so there is a white triangle between the red flow.
This one?
No, it's at the above, here on the right.
This one.
Yeah, and then the other graph.
Actually, we are presenting the non-dimensional temperature, which is generally opposite to the in calculations. Like in film cooling, it's like temperature. So temperature is is opposite to the film cooling effectiveness representation. So higher the film cooling means it will be in terms of the non-dimensional temperature. It will appear like red colors.
Okay. So one final question. You have shown also some examination of the thermal stress.
Yeah.
So are you working here together with an institute specialized for material science, or how do you want to use this data?
Actually, we are getting some of the CFD result, so temperature profile,
Yeah.
and the selected domains, and we are just using the temperature what we are obtaining through the CFD. And before CFD we did some experimental to validate the CFD methodology. After that, whatever we are getting through the CFD, we are just using the temperature profile for the specified material which is mainly used for the afterburner, like Inconel 738, and using their property of Inconel 738 and using the temperature profile boundary condition, we are trying to calculate the thermal stress.
Yeah, and so for what do you need this? What is then the usage of this thermal stress? Do you want to change the material, or to optimize the material, or is it just an additional information?
So, and what we got actually, that in case of reverse ejection, the cooling is more uniform. So we are trying to show that in reverse ejection the cooling is more uniform, and because of that there is a significant reduction in the thermal stress. So the life of the component will be more if we are doing the means reverse ejections. So basically the ultimate aim is to protect the component. So in that way it is better actually.
Okay. Thank you.
Okay, thank you.
Okay. So do you have any questions concerning the lecture, concerning the question we shall discuss today? Or it's 5 o'clock in the afternoon, and we can stop for today. Okay, so Professor Sahoo, we can finish for today.
Yeah.
Okay, thank you.
So you presented? Yes. Okay. Any other things?
No, there were no questions.
Now my thing is that